morning, ladies and gentlemen. Welcome to the SAMC program on quasi-Monte Carlo methods and high-dimensional sampling in applied mathematics. I'm Ilse Ibsen. I'm an associate director of SAMC. So first of all, many of you may not know SAMC. So what we are one of the 8 institutes funded by the US National Science Foundation, and we are basically just a grant. That's all we are, a grant. And the grant is awarded to 3 universities here in the Triangle: University of North Carolina, North Carolina State University, and Duke. So those 3 universities form a triangle, and SAMC is in the center of the triangle. And we are located in North Carolina, so you see a picture of the United States East Coast, so you have some idea of where we are. So SAMC was established in 2002, and we were just renewed, so we have another funding cycle until 2020 when we will recompete with the whole world for existing yet longer. So our mission is a mouthful, but basically it amounts to bringing statistics and mathematics together with the domain sciences to solve really hard problems, data, model-driven problems. That's our mission. So there are a couple of us on the directorate. We're still looking for an associate director from Duke. So in terms of what can we do for you? So in terms of research, we have year-long research programs like this one on quasi-Monte Carlo methods. We also have shorter summer programs, and we have topical workshops throughout the year. And we also have an education and outreach component, graduate student workshops and undergraduate student workshops. So with regard to research programs, they have several components. So the biggest components are the working groups. We will talk more about working groups. Working groups are people together doing research. And we make it a little easier by supplying you with a virtual meeting system and with phone numbers so that you can meet every week. And by meeting every week, the hope is you'll have something to show for at the end of the year, like papers, proposals, and all that. We also have research workshops, we have summer schools, and we have participants, visitors, SAMC postdocs. You will meet Cheng and Matthias Sachs here, who are the postdocs associated with the QMC program. And then we have a ton of participants like you guys. So with regard to the current programs, we have 2. One program on climate started already last week, and then ours on quasi-Monte Carlo methods. So these are the 2 year-long programs we have this year. So then for next year, we have a program on model, on uncertainty quantification, in statistics and mathematics, and one on precision medicine. And then for the following year, we are still discussing what's what. So with regard to the education and outreach component, we have undergraduate workshops, one in October, which will be associated with the climate program, one in February, which will be associated with the QMC program. So if you have some good undergraduates, alert them to apply to the workshops. The undergraduates come from all over the US. We also have a 5-day undergraduate workshop in May. And then we have a graduate student workshop. I'd like to talk a little bit more about this on the next slide. And then we get together with the other institutes on their modern math workshop and Field of Dreams workshop. So the industrial mathematical and statistical modeling workshop is for graduate students. It's a 10-day workshop where we try to simulate industry. So the students ideally would be in their 2nd or 3rd year when they are thinking about whether to go into academia or into research. And we have 6 projects, and students work in teams. And the projects are presented by people from industry or the labs. It's a very intensive workshop. It's a lot of fun, and often papers come out. But it helps students to find out a little bit what goes on in industry and whether they would like that. And we are really happy to receive proposals from you guys on SAMC programs, especially because we haven't decided yet what to do for the year after next one. So, you're welcome to talk to me or to Richard Smith, the director, who's sitting in the last row. So we are also very happy to take your money. We have a sponsors program. There is, in your packet, there's a letter to your department. So if your department would like to donate money, we are also very happy to take your department's money. The funding situation is getting worse and worse, especially from the National Science Foundation. So we have to start standing on our own feet, and every little bit of support helps. Oh yeah, and we are also doing communications. So Rick Scoggins, who is there, is our communications director, and he's really good at making sure that the world out there sees SAMC. So we have a number of platforms. Rick will be taking pictures. Rick will be happy to listen to your stories and recruit you to write something for a blog. So anything that we can give to the world out there to tell them more about what SAMC is. So now with regard to this particular program, we have 4 program leaders. Without these guys, nothing would have happened. In particular, Art Owen, who was the driving force behind the program. Fred Hickernell, Francis Kuo, and Pierre Lecoyer. All of them will give talks today, and these are the guys who made the program. I just assisted a little bit, and we have also a number of local faculty, Nicholas Fryman, Tim Kelly, Jianfeng Lu, and Jonathan Mattingly, who will be participating. So currently we have 5 working groups, but we are hoping for a lot more. I will say more about working groups, what they mean, how they get together this afternoon. But it's basically people getting together, working on research topics they're interested in. That's what that is. So we have 5 at this point, and we are requesting ideas for more working groups. So please see me or one of the program leaders. We are very, very happy to get your suggestions. We have a number of future workshops coming up within this program. So there's a workshop in December at the very same location here on Monte Carlo methods, organized by Jianfeng. There's a workshop in April at the Turing workshop, which is organized by Tim Sullivan and Chris Oates, who are somewhere here. They'll be talking. So if you're interested in that, it's basically a workshop for their working group on probabilistic numerics. But they are very open-minded guys, so if you want to attend, I'm certain they'll find a place for you. And then the transition workshop in May is the official ending of this program, but it's also, it's an opportunity for the junior people and the working groups to show the results and to think about how to continue collaborations beyond this program. So the plan for today is we will have our program leaders, and Clementine will give 5 tutorials. That will be something to look forward to. We will be live streaming the tutorials, so we have to make sure to stay on time because of the live streaming. So Art and Pierre will give a tutorial, then there'll be lunch. You'll be on your own. There are a lot of establishments here at on Duke campus where you can have, we can get something to eat and coffee very, very close by. Then there'll be the tutorial by Fred, and then I will say a little bit about the working groups. Then Francis and Clementine will talk, and then tonight from 5 to 7 is the poster session with the reception. Please see the underlying under reception. Reception means appropriate libations and food will be supplied as an incentive to attend the poster session. That's what that means. And then at 7 o'clock sharp, the shuttle will take you back to the hotel. So, and if you have questions, we have an outstanding SAMC staff. There's Sue, or probably you already talked by email to Sue, who is the workshop coordinator. There's Karem, who is here. She's really efficient. Thomas is the staff person from the NC State side. Rita, you will probably talk to her afterwards with regard to reimbursement. And then there's Rick, who does all the communication stuff. So enjoy the workshop. So now, okay, because of the live streaming, we have to wait 5 minutes before I can introduce Art. So we'll just have a 5-minute break. today. It is my very great pleasure to introduce Art Owen as the first plenary speaker and the one to kick off the official opening of this year-long program on quasi-Monte Carlo methods. Art is on the faculty of the statistics department at Stanford University and has basically been there since birth. He has spent most of his professional life at Stanford. He's a fellow of the American Statistical Association and an elected fellow of the Institute of Mathematical Statistics. Art's research interests include Monte Carlo and quasi-Monte Carlo methods, and he has lots of research interests, but also empirical likelihood. He has co-authored 2 books and published numerous papers in both mathematics and statistics journals. Art has a long-standing workshop with another workshop series, the QMC workshops, and he organized the most recent workshop in Stanford in 2016, and that's actually where this program really got going, where we had a planning workshop. So Art has been the driving force behind this SAMC program. So without him, we would not be here. So I've already seen Art's slides, and I can tell you that they're really exciting. And as usual with Art, it's crystal clear introduction to quasi-Monte Carlo methods. So let's welcome Art.
Well, thank you, Ilse, and thanks for those kind words, and thanks for making this thing possible. Okay, so I'm going to introduce quasi-Monte Carlo, and I'm not going to assume that you've seen a lot of it before. So it's really quasi-Monte Carlo for first-timers, and also I'd like to tout the next QMC will be in Rennes next summer. Okay, so in Monte Carlo or quasi-Monte Carlo, we're sampling. And usually we use random points in a Monte Carlo, and we try to sample the input space of some function. And if you just use plain random points, you're in the upper left-hand corner. Now, there are times when you just don't want to use plain random points. You maybe do a little bit better, put some structure. A lot of people would sort of harken back to what Fubini says and use a grid up there. And the point about quasi-Monte Carlo is you can do a lot better than random points, and you can do even more better, I think, than a grid. Grids are seriously problematic once you get past like a few dimensions. So some of those other things up there, the third from the top is a quasi-Monte Carlo point set. The fourth one in the top is a different kind of quasi-Monte Carlo point set. And then the next 2 are also quasi-Monte Carlo point sets. This one here, the second last, is called a sparse grid. I don't think any of the tutorials will tell you about that, but they're interesting points. And then the one on the bottom right, those are called blue noise points, and computer graphics people like those. They have those points are trying to not get too close. There's like no touching rule for the points in blue noise. So here's an outline of what I want to tell you about. First of all, like, what is quasi-Monte Carlo? And from a statistical point of view, you would think of it as stratification just taken to its utmost limits. Then I'll explain some of how quasi-Monte Carlo works and why it works, and give you a couple of the constructions, but by no means all. Then I'll tell you about randomized quasi-Monte Carlo. You can get maybe the best of both worlds of Monte Carlo and quasi-Monte Carlo, and a little bit about why it works, when it works. And then the last 2 items are things that I probably won't get to talk to you about, but maybe you can capture me during a coffee break. You can actually stick quasi-Monte Carlo into Markov chain Monte Carlo, and you can use quasi-Monte Carlo on some methods that use particles. So, those aren't quite introductory. Okay, actually before I go to that, I want to say that the quasi-Monte Carlo community, it's a mix of people doing mathematics, people doing computer science, and people from statistics. And what you see are the toolkits that people use from those areas are different but overlapping. And then the priorities and outlook, they're different but overlapping. So there's a lot of chances to learn from other ways of looking at things. If you look at where Monte Carlo methods got famous, there are a number of landmark papers. So Metropolis paper, somebody figured out, we can just Monte Carlo this physics problem. Bootstrap sampling and Markov chain Monte Carlo, chemistry, computer graphics. There are a lot of places where a huge breakthrough happened when somebody first figured out, hey, we can do Monte Carlo for our problem. Well, I think there are more of those landmarks coming for quasi-Monte Carlo. As yet, there's particle transport methods. People have figured out that QMC really works on that. And financial valuation and computer graphics. And I'm quite excited about some recent work on solving PDEs with random environments. But I think we should at least get to a top 10 list of sciences and engineering disciplines where quasi-Monte Carlo is now, will be a major thing. And so I think there's more of them out there to be found. And where do I think they'll come from? Well, you can't really tell. But I would suspect that machine learning is a good candidate. They use Monte Carlo in lots and lots of places. Some of them will probably benefit from quasi-Monte Carlo. Bayesian statistics, a lot of Monte Carlo there, room for quasi-Monte Carlo, I believe. Uncertainty quantification is another one, and Clémentine Prieur will be giving a tutorial on some sensitivity indices and uncertainty quantification methods. Okay, so, and then once we have, of course, once those landmark applications show up, they typically stimulate new fundamental research in the core of quasi-Monte Carlo itself. Okay, so where's the next landmark going to happen? Hard to say, but the best way to find out if your problem will become a landmark in quasi-Monte Carlo, the very, very best way is just do it. Okay, sometimes you have to switch from planning what to do to doing what to do, and trying it is the easiest way to find out if it works. Okay, so here is a simplified version of Monte Carlo. We have what we want is this integral, and what we have is this sample estimate of it. And in plain Monte Carlo, we just take them at random. And quasi-Monte Carlo, we try to spread them more evenly. Okay, this is an expectation with respect to a uniform distribution on the cube. But you can be much more general if you take a mapping from the cube to real space where uniform here gives you the distribution P there. And there's an astonishing number of tricks for this in the book by Luc Devroy. So many, many problems. It's not just the unit cube. Okay, so here's what the points look like with Monte Carlo. If you use a Fibonacci lattice, you get these. Pierre Lécuyer's tutorial will be on lattice methods. I will not be saying much about lattices. Here is a Hammersley sequence, which is a digital construction like the ones I'll be showing you in some detail. And Monte Carlo points, they're always going to clump up somewhere and have gaps somewhere else. It's random where they show up, but they will be there. And quasi-Monte Carlo tries to avoid clusters and gaps, constrained only by the mathematics of what's possible. Okay, well, you can state the goal this way. We want our points to be nicely covering the unit cube, so we want the discrete uniform measure on these endpoints to be really close to the continuous uniform measure on their domain. It's a fundamental thing in mathematics where you have a continuous thing, but to compute it, you have to approximate it by a discrete thing. So this is what we want. This discrete uniform should be really close to that continuous uniform. So we want a distance between two distributions. Here a continuous, there a discrete. And there are lots of ways to tell the difference, and those are called discrepancies. Okay, so here is the most widely studied discrepancy, by no means the only one. So we have this unit square, and we feel like the box anchored at 0 up to a point A, it should get its fair share of the points. So here's a box. It goes along 0.6 and up 0.7. So it's got 42% of the area of the square. So it really deserves 42% of the points. Well, it got 13 over 32 of the points, and it deserved 42, so it came out a little bit light. That's a discrepancy. This function is the local discrepancy function. And if you take the sup norm of that thing, you get the star discrepancy. In one dimension, this is Kolmogorov-Smirnov. Okay, so we would like that to be small. Now, there are lots and lots of discrepancies. So up here again, that's still the star discrepancy. And it pays special attention to the origin, but you don't have to. You can take a discrepancy over all boxes. And in fact, you can take wraparound discrepancies, discrepancies over triangles, rotated rectangles, balls, convex sets. There's a lot of discrepancies out there. Another thing you can do, instead of taking the sup norm of the local discrepancy, you can take an LP norm. Okay. So there are many, many things that you can do. And the best results are pretty much only for axis-aligned hyperrectangles. Okay. So that's where it gets really good. Okay, so in Monte Carlo, there's a law of large numbers. If you sample far enough, you will get the answer, or you'll converge. The same is true in quasi-Monte Carlo. If you have a Riemann integrable function and the star discrepancy vanishes, then you will converge to the right answer. Okay. But how fast does it happen? We don't want to just know that it's going to get there. We want to know, like, are we there yet? Or how far are we for a given n? In Monte Carlo, there's a central limit theorem. In quasi-Monte Carlo, there's a Cox-Mihalkovka inequality. So I'll show you first the one-dimensional version due to Coxma. So d is 1, and what you get is that your error is no more than the discrepancy of your points times the total variation of the function. So this is your error. That's how good your points are. That's how bad your function is. And quasi-Monte Carlo has lots of these sort of inequalities. You take how good are your points, multiply it by how bad is the function, and that's an upper bound on your error. So this is an archetypal inequality. There's lots and lots of them. Okay, and I'll give you a taste of the proof. If you write the integral of f and then do integration by parts, you get that. There's a corresponding summation by parts. You take, there's your quantity you want, there's your estimate, and you do a summation by parts. Now, if you subtract them, this will cancel. And then inside the summation by parts, this difference between f here and f there, that's just an integral of f prime. And so if you make that substitution and plug and chug, you'll get this inequality, you'll get this result that your error is the absolute value of this integral. It's an inner product of your local discrepancy and your derivative. And then now you can apply Holder inequalities or whatever you want. And the star discrepancy is the sup norm, and the variation is the L1 norm of f prime. Okay. Okay, now, what happens in d dimensions? In d dimensions, you get the Cox-Mihalkovka theorem. And really, all that changed is that the integral is now over the unit cube in d dimensions. And, oh, wait a minute. Discrepancy, that's the same as it ever was. Total variation is different. So in d dimensions, the total variation is a little bit more complicated than one dimension. There's about 12 different ways to define it. And the one that we use in quasi-Monte Carlo is the total variation in the sense of Hardy and Krause. And multidimensional variation, there are the few surprises. If you're used to the one-dimensional total variation, the multidimensional one doesn't work the same. And I won't explain it in this tutorial just for time purposes, but I can talk to you about it over a beer napkin or a coffee or whatever afterwards if you want to know. There are some surprises, and I'll point a few out. And then a puzzler is, well, look, this is like, there's no 95, 99, 99.9% there. That's like 100%. So you could ask yourself, is that a 100% confidence interval? And then what could be better than 100%? Like, you can't have 101, that's for sure. Okay, what about rates of convergence? You can make this discrepancy vanish at this rate, log n to the d minus 1 over n. which is usually written as, well, it's little o of n to the minus 1 plus a smidgen. That looks a lot better, at least, especially if you write it this way. It looks a lot better than n to the minus a half. But what about all those logs? So if I take log n to the power 40, that could be problematic. Well, you could, for any n that you can afford, it's possible that this quantity is way bigger than that, and the constant might not be better here either. Now, the reason this doesn't really, a couple reasons why this isn't a problem. Low effective dimension can counter those logs. And some ways of randomizing it also kind of wipe out the problem of the logs being log powers being huge. Incidentally, if you can reduce that exponent, we would greatly appreciate it. Okay, so this is like the biggest outstanding problem in discrepancy is how small can that get? Now, you can't make it as small as d minus 1 over 2. You can make it as small as d minus 1. And what about what's going on in between? And so that's a lot of ongoing effort on trying to solve that. I'd like to point out that the Coxwell-Hofke inequality is tight. Okay, you can't get 1 minus epsilon here. There is a function that will make this an equality. Okay, so it's a tight inequality. It is also a loose inequality. So the mathematical definitions of tight inequalities allow them to be loose as well. So it can be very loose. It's because it's a worst case. It's a worst case. So suppose an adversary saw your points and then chose an integrand to make your error as large as possible for those points. Well, Coxwell-Hofke would cover that case too. So it's a little bit conservative. Just like in statistics, we're familiar with Chebyshev's inequality. Chebyshev's inequality would tell you the chance of a normal observation being above 10 is below 1%. And it truly is substantially below 1%. So this is loose. But it's also tight if you pick the, you can pick a distribution to make it an equality. So our error is an inner product between the local discrepancy and f prime. And if somebody gives you an f prime that's proportional to your local discrepancy, then you're in a bad way. Okay, so multidimensional variation has a couple surprises. So here's maybe the primary surprise. Let's look at a function of two variables that's 1 below the diagonal and 0 above. That has infinite variation in the sense of Hardy and Krause. Okay. So it's not what you would normally think of as a function with infinite variation, but it does. Then, however, it can be approximated by some other function that's got finite variation. And more generally, if you suppose you have a cusp. So let's just take the positive part of A transpose X. Well, that will have infinite variation in 3 dimensions or more. Suppose we smooth it, like the square will be have a smoother discontinuity or a smoother issue. Well, then it's got infinite variation in dimensions 4 and higher. Okay, now you can actually have an axis parallel discontinuity will have a finite variation. Okay, so there are a couple of surprises for us in variation. Okay, so now let's look at extensibility. If D is 1, the best way to place your endpoints is to have them equispaced on a midpoint rule. That will give you the minimal star discrepancy. But if you did that, where are you going to put the next point? Your n plus first point won't still be equispaced. So you have to slightly break the pattern when you put the next one. And you can't actually get discrepancy 1 over n along an infinite sequence. So there's quite a bit of interest in extensible sequences. So you have an infinite sequence of points, and then wherever you stop it, the discrepancy is bounded by log n to d over n, and you lose 1 power of log n in order to get extensible. So here is the first and easiest quasi-Monte Carlo construction. And you can assign it to a class of students and just have them do this on their own. The code ends up being really, really short. So this is a van der Corput sequence, and suppose n is 1. You're only allowed 1 point in the unit interval. You probably want to put your 1 point at the middle. Now you're going to put the second point. Well, you could stick it in the middle of the left hand or the right hand interval. Let's go left. Then the next time, well, we better put it on the right hand to balance. And now we have 4 equal intervals. Where are we going to put the 5th point? We have to split one of them. Let's split this one. Now we split something on the left that time, so we'll split something on the right this time, and then we'll split the next one on the left, and then the next one on the right, and carry on. So that's the van der Corput sequence, and if you had to do it one by one, you might come up with something like that. So here's how van der Corput works mathematically. You take the integers and write them in base 2. Okay, so 5 is 1, 0, 1, and then you reflect them in the binary point. So 1, 0, 1 becomes 0.101, and 1, 0, 0 becomes 0.001. And then your points are 0.1 is a half, a quarter, 3/4, 8, 5/8, 3/8, 7/8, etc. And here they are. And the reason this works so well, the integers alternate between odd and even. And therefore, these points alternate between being to the right of a half and to the left of a half, right, left, right, left, right, left, as it goes odd, even. And if you take 4 in a row, well, the last 2 digits go through all 4 pairs. And so any 4 consecutive points will be stratified in intervals of length 1/4, and you get the same thing for 1/8, 1/16, etc. That's why it ends up being very, very nicely spread out. And people usually start, it's often started with the first point at 0, not at 1/2. Okay, so the next step up is the Halton sequence. And here are the first 72 points. We'll do the van der Corput on this axis, and we'll do the van der Corput trick in base 3 on that axis. And then we get points that are so nicely distributed. We have 8 boxes here, 9 boxes there, and all 72 squares get 1 point. And if we carry on to 864 Halton points, we filled out the square like so. And if you had 864 random points, they wouldn't look quite as nice as the Halton ones. And here's how it works. You take the integer I and you write it in base b with these digits, and then you use those same digits in the reverse order. So instead of power b to the k, it gets power b to the -1 minus k. And then you take, say, base 2, base 3, base 5, base 7, up to whatever prime you need. And so that's something you could definitely have a class, a graduate class or even an undergraduate class, implement that and try it out. It's not very hard. One of the issues with the Halton points is that they are, they're nicely balanced if you have a multiple of a power of 2, 3, and 5, but it's awkward to balance multiple dimensions at once. If you could use the same base on all dimensions, you'd be better off. And so that's what digital nets do. And digital nets balance what are called elementary intervals. If we're working in base 5, we can slice the square into 5 equal pieces. And we can slice each of those into 5 pieces and get 25 pieces. And of course, we could slice it horizontally, or both ways, or we could slice it 5 in this direction and 25 in that direction. And this is just the upper 2 by 3 corner of an infinite grid of pictures like that. Here is an elementary interval. It's integer to integer plus 1 divided by a power of b. And a 0 MS net is such that every elementary interval that deserves 1 point gets 1 point. Okay, so if its volume is 1 over n, then it gets 1 point. TMS nets have a quality parameter t bigger than 0, and anything that deserved b to the t points gets b to the t points. So you'd like t to be small, but you can't always get that. And so given the dimension, the sample size, and the base, there are bounds on the t that you can get, and there's a nice website that has all of those. Here's Here are some illustrations of a couple of digital nets. So this is a base 5 net, and the reference lines show you how it's stratified. Here's that extended version of that net, so the 625 points here. And this 625 points are actually from a 5-dimensional net that's projected down. Okay. Oh, I don't like those stripes. We can get rid of those stripes. I'll show you later that something that gets rid of those stripes. They don't look quite right, and you can remove them. So this net here comes from 625 points in 5 dimensions. There are over 43,000 elementary intervals in that cube. And somehow with 625 points, you can balance all 43,000 plus of those sets. So that's an astonishing amount of stratification from just that many points. And the number of strata grows faster than the number of data points. How does this kind of construction work? It's a little bit like van der Korp. So take the integer I and write it in base b. And we get these coefficients ai, k for the ith one. And make a column vector out of all those a's. Now multiply it by a strategically chosen matrix, modulo b, and take the resulting vector of base b digits and turn it into your x. Okay, so this is a little bit like the van der Korp-y thing. Then you have to make a judicious choice of these matrices. So this will do the first xi1, and then for xij, you pick a new matrix, but you take the same vector of digits. Okay, so these monographs will give you some ideas of how one would pick an appropriate matrix. You can't expect good results from an arbitrary matrix. And the computational cost of this is actually quite low. It's really not going to be much bigger than if you just ran a random number generator. So QMC is kind of at the same cost as MC. Okay, so now let's look at some extensible versions of these nets. So an extensible TMS net is known as a TS sequence. Okay, so we drop the m because we're going to do all possible m's. So let's take a TMS net, and then another one, and another one, and another one. And we have an infinite sequence of TMS nets, here, here, and here. And if you group together b of them, you get a Tm plus 1 S net. And then the next b will make another m plus 1 net, and so forth. And then m plus 2, m plus 3, m plus 4. It's actually astonishing that that kind of thing even exists. But there it is. And the famous examples, the one by Sobel in base 2, Henri IV has one with t equals 0, but the base grows. And Niederreiter and Cheng have maybe the ones that achieve the best level of t so far. Okay, and I'll say a little bit about lattices. So this is the other main family. Lattices, you can look like, this one's not very good. This one's better. This one's much better. And you can, by carefully choosing these integer constants here, you can try to get a better lattice instead of a worse lattice. Okay. But Pierre will tell you a lot more about lattices. Okay, so how do you estimate your error? It's nice to get a number, but you want to know, should you trust it? And the Coxwell-Hofka doesn't actually give you a confidence interval because that upper bound is not a known quantity. All you know is that the error is less than this product, and that product is less than infinity. So you know your error is finite, but you knew that before you started. So it's not actionable. A confidence interval has to be something that you can actually compute. So it tells you that as you increase n, things are going to get better, but for your fixed n, it really doesn't tell you anything. And there's also a slight problem that, well, if you had this function, then, then the variation is infinite, so now your error is less than or equal infinity. It's just not very actionable information. The other thing about Coxwell-Hofka is it can be very conservative. It's a worst case. I'll just give a shout out to the Gale project of Hickernull. and many others, where there's you tell it the epsilon you want, and it will keep sampling until it's confident that that you've achieved that error or less. Okay, so I'll tell you now about randomized quasi-Monte Carlo. In randomized quasi-Monte Carlo, we make the individual x's uniform, while collectively there's still low discrepancy. Now, you can repeat the process r times and average it, and you can estimate the variance by seeing how different those are from each other. And now you have at least a sample-based estimate of your accuracy at the very n you're using and for the very function f you're integrating. And if you have finite variation, then your mean squared error is like order n to the minus 2. Simplest way to randomize is to take your points and add a uniformly distributed random shift to them. So here's this uniform vector. We add that to all the points and just keep where they ended up. And that's pretty easy to do. It's commonly used. Also, it means that you won't have a point at the origin. Maybe you didn't want one at the origin because if you're inverting the normal CDF, it's bad luck to put a 0 in. Another way to randomize a quasi-Monte Carlo point set is by scrambling. So suppose that you're dealing with a 3-dimensional cube and you have a net in base 4. You can chop that cube into 4 slices and shuffle them. And then you take each of those slices, chop it into 4, and shuffle. And carry on ad infinitum to all levels. And then you do that not just for this axis, but for the second and the third axis. Now, if you've done that, every point winds up uniformly distributed. It had a 1/4 chance of being in each of these 4 slices, a 1/16 chance of being in each subslice, etc. So this axis will definitely be uniformly distributed, and it's independent of that other axis. So you're uniform on the cube. But if you had a net in base 4, you're just moving those chunks around, and you will still have the same. You're moving elementary intervals around, but you're not really changing how many points are in. You're not destroying the digital net structure anyway. How does that work? Well, if your original points have this base B expansion, then your new points have that base B expansion, where the digit A turned into A tilde, where A tilde is a permutation of the base B digits of the thing you started with. And the permutation here depends on J and K. It can actually also depend on everything, all of the upstream digits. That's the fully nested scramble. You can use simple random permutations. So there are other random permutations that are pretty advantageous, and Matusek has some beautiful work on linear permutations, nested linear permutations. The simplest thing you can do is a digital shift, where you take your old digit and you add some uniformly distributed bit to it. Okay, so that's in base 2, you're doing a bitwise XOR of your points. Okay, so here's some examples. The points shown here are the first 530 points of a 4 sequence in base 53. And so after you apply a digital shift, you get, well, it doesn't look that good. The digital shift doesn't do that much to them. It's almost as if you had done a rotation of them. However, if you apply a random linear scramble like Matusek does, you do manage to smash the structure up. You can still see some striping and clumping. And the nested uniform scramble gives you this. So it's still a 0.53 net, but it doesn't seem to have the obvious patterns. Okay. These two end up giving you the same variance, and this one requires less storage to do. Here's some fun facts about the 4 sequence. If you don't scramble the 4 sequence, there's some odd low-dimensional projections. So if you take, well, here we have x4 plus x6 minus x10 minus x11. On this axis, it's another linear combination of 4 of those things. And they plot as a 3 by 3 grid. here's another couple of linear combinations that plot like corners of a hexagon with a point in the middle. Now, if you randomize the 4 points, it smashes up that structure. Here's a Sobol set. Here are some projections of 1,024 Sobol points, second versus first. Sobol is all in base 2, and some high-dimensional projections don't end up looking that well. And then when you double the sample size, it might actually then fill in this whole block the next time. If you scramble Sobol points, you move the empty blocks around, but you don't. The scrambling doesn't fill them in. Okay, so what do you get from scrambling? Well, if your function is in L2, then the variance on scrambling is small o of 1 over n. Okay. Even if there's infinite variation in Hardy-Krause, you will get a better, you converge better than Monte Carlo. How bad could it be? Well, the variance can never be more than some finite multiple of the Monte Carlo variance. So that kind of gets rid of the problem of log n to the power 40. This constant can be, is some constant. It might not be that big. If t equals 0, the constant is no more than 2.718. It's no more than e. So you can feel that you're not going to be much worse than Monte Carlo, and asymptotically you'll be better. And if the function is smooth enough, then you actually get a better rate of convergence for the variance over a scrambled net. How does that work? Well, here's some intuition that Fred Hickenroll pointed out to me. Suppose we just have a tiny little QMC net, and we start off with van der Korpet, and it's the 4 left endpoints. If we do a random shift, everybody moves, say, 3 steps to the right, and then your errors in these 4 intervals are correlated with each other. The scramble ends up giving you independent random samples from each of those 4, and then you get a little bit more error cancellation. Okay, so there's some new developments or recent developments, higher order digital nets. Joseph Dick and mostly Joseph Dick, but also he had student Baldo work on this. You start with a net, say, in double the number of dimensions, and you take 2 of the variables and you interleave them to make a new one. So say here are 2 of the variables from your first net, and this one has a decimal expansion with g sub k. This one is h sub k, and then you just interleave. You go g, h, g, h, g, h. And if you do that, you can get n to the minus 2 plus epsilon, or randomizing it, n to the minus 2 minus a half plus epsilon. And you can interleave even more than 2 if you want. So you will get much more accuracy if there's the smoothness. It is kind of costly. You have to take twice the dimension of your net, or 3 times the dimension of your net to make it work. So it's now being used in some work with quasi-Monte Carlo problems for PDEs in random environments, and the tutorial of Francis Kuo will explain some of that. Okay, let's see. Cursive dimension. There's classical results of Bak-Waloff. If your function has m derivatives, it's got r derivatives nicely bounded, then Bak-Waloff can find, if you give Bak-Waloff some points, he can find a function where your error is at least this large. If instead you don't tell him where your points are going to be, but you tell him what your randomization rule will be, he can make your root mean squared error at least that large. Okay, so this effective dimension is pretty unfortunate. And what if we beat those rates? So sometimes we actually find to our surprise that on a high dimensional function we get high accuracy. We didn't actually beat the cursive dimension. Bak-Waloff never said we're going to always fail. He only said that we can't always succeed. And so what it means is that we had a function that just wasn't that hard. And there are different ways to say that the function isn't that hard. One way is, well, maybe only the first few components really mattered. Or the other is, maybe it only mattered a few at a time. Like maybe it's sums of 1- and 2-dimensional functions. So if we can decompose our function into a sum over all subsets of indices of something that only depends on that subset, there are many decompositions that do this, then we can apply Cox-Mihalowska term by term. And if we're lucky, our low-dimensional projections have low discrepancy, and our high-dimensional projections have low variance. And so we're always multiplying either small times big or big times small, and then we can get a small error. Okay, so that will, if that is your situation, then you can end up with a good accuracy. There are a couple ways to describe this. There's a lot of work on weighted Sobolev spaces and tying into tractability, and then there's methods based on ANOVA and effective dimension. They're not lifting the curse of dimensionality, they're just explaining how come it came out so well for us. I'm pretty interested in fusing these two ideas together, and they both leave gaps. This one leaves the gap of what weighted space should you choose. This one has an issue that ANOVA itself doesn't, the projections might not be smooth. Okay, and I'll give you a taste of weighted spaces. Okay, so, and Fred Hickernall's tutorial will tell you more. So here we'll take this partial derivative where we differentiate once with respect to every xj that's in the set U. Okay, so we're not going to differentiate. Here we won't differentiate twice with respect to anybody. Everybody gets 0 or 1. And then here is a norm, a weighted norm. And what we do is we sum over all subsets, and we have 1 over that weight, integral over all the points xu of that subset, and then an integral over a complementary set, a partial derivative with respect to u. Okay, so then there's this norm, and you can make a function ball, all the functions where that norm is below some radius. And let's see, let's interpret these weights. If gamma u is small, then it's in the denominator. So if gamma u is small, this quantity can't be big if your function is in the ball of functions. So we're putting either high weight. If gamma u is high, we're putting high weight. If it's small, we're putting, say, a high penalty on that aspect of the derivative of the function. Okay, so there are numerous ways to choose these weights. The simplest to think about, you just take a product of weights over the elements of the subset. But there are many others, and there's a survey paper by Dick, Kuo, and Sloan that explains many of these. Okay. The way ANOVA works, if you're familiar with the analysis of variance on discrete tensor product spaces, it's the same idea in the continuum. And so you can get main effects and low-order interactions. And if the function is dominated by the low ones, then quasi-Monte Carlo and randomized especially can really help. We say that the function is basically S-dimensional if the first S variables capture 99% or more of the variance. 99% is a little bit ad hoc. But it's motivated by, if you can tell somebody that you can get a 100-fold improvement, then they probably should pay attention to you. If you're giving them a 20% improvement or a double thing. But who's going to ignore a 100-fold improvement? So this is geared to the fact that, when this happens, maybe you can get a 100-fold improvement. This is the low order. These are, like, say, the first S variables dominating. And this is where the variables taken up to S at a time dominate. There's a related notion of the average dimension where you take the ANOVA variances and weight them by the cardinality. And if that comes out like 1.05, then you know it's a low-dimensional function. Okay, so the open problem I like to talk about to people here is, can you use the ANOVA sampling methods to figure out what weights you should have? And there's reasons to believe that might work, and there's also reasons to believe that it can't help. So basically, we just don't know. But there's work on Sobel indices, active subspaces, there are kind of approaches. Can you tinker with your function and figure out what weights you should have used? And can you do it in a cost-efficient way? OK, so I mentioned this. When we do this, what we're doing is the weighted spaces and an effective dimension, they're really describing a case where everything went well. But why leave it to chance? Can't we just make it work well? What if we engineer the function to have low effective dimension somehow or other? There's quite a bit of work on that. You try to cram the importance into, say, the first few components. There's a lot of work in this where you're simulating Gaussian. So we have a Gaussian with mean 0 and variance sigma. We take some uniforms, turn them into standard Gaussian, pre-multiply by the square root of sigma. But there's different square roots of sigma. And you could use a principal components or a Brownian bridge or some other methods. And the best sigma can depend really strongly on what you're trying to do. There's some work by Papagiorgio showing there's no universal sigma that you should use. So this is different. In Monte Carlo, it wouldn't matter what sigma you used. In quasi-Monte Carlo, it makes a lot of difference. Here's a picture. Suppose you're trying to simulate a Brownian path. Well, your first variable might just give you this. And your first 8 variables might give you a skeleton. And then you can just refine the skeletons with more and more random variables. And depending on the integrand, the first things in might really dominate. And then getting those stratified will do what you want. There's also some related work, Mike Giles and many others, on multi-level Monte Carlo. OK, so I think I have a couple minutes to tell you about a few not quite tutorial things. So what about Markov chain Monte Carlo? If you look around the world, people use Markov chain Monte Carlo a lot. They usually use it on problems where you actually can't do plain Monte Carlo. So can you do Markov chain quasi-Monte Carlo? Or can you do it well, or should you do it? Well, in a sense, Markov chain Monte Carlo is like the transpose of a QMC quasi-Monte Carlo problem. So most of the time in quasi-Monte Carlo, we have a modest number of dimensions and a number n that's just growing way faster than the dimensions. In Markov chain Monte Carlo, we basically have an infinite dimensional problem. And we maybe take one or a small number of replications. So they kind of look, it just looks like one is the transpose of the other, which makes you think, how can you possibly put these into that? And where QMC is based on equidistribution, MCMC is really driven by ergodicity ideas. And you can sort of do it. So first of all, you feed your Markov chain Monte Carlo IID uniforms. That's the usual thing. What if you fed them something balanced? So just take away their stream of random numbers and give them something else. Well, you can't just plug in plain quasi-Monte Carlo points. It will fail. It will fail in a way that's actually really funny to look at. So it's, you just don't want to do that. What you need are that all the consecutive k tuples have low discrepancy out of that stream. This is exactly what people ask for when they design a random number generator. That's one of the criteria. So what you can do is take a small random number generator and use it to the last drop. Just use every number out of that random number generator. Go through one complete period. And that will give you some, there's some work on doing QMC with that. OK, so sequential quasi-Monte Carlo. Just give you a taste of that. Matthew Gerber is here. There's some very exciting work putting quasi-Monte Carlo into particle methods by Chopin and Gerber. You have a bunch of particles, and you follow them through time steps. When you want to get to the next time step, you need a matrix of uniforms. Well, why not use a quasi-Monte Carlo matrix instead of a random one? Then when you get to the next time step, you can feed it another matrix of uniforms. But you sort of want those to be independent of the position that it got to. And that's pretty hard, because they just got spread out through d-dimensional space. And then you want your next step to be balanced with respect to where it wound up in d-dimensional space. And it's easy when d equals 1. You can just sort them. You can put another column in there and use that to align your old points with your new steps. But if d is bigger than 1, it's really hard. There's previous work by Lecuyer and others on array QMC. The Gerber and Chopin thing, what they do is they run a d-dimensional space-filling curve through the points, and then they save one QMC variable to align with that. Okay, so I've obviously skipped a zillion details on that. I think it's pretty exciting and cool, and it'll be interesting to see where that goes. Okay, so I want to thank a bunch of people. First of all, the National Science Foundation supported this work. The leaders of the program, there's Fred Hickernow, Francis Kuo, and Pierre Lecuyer. They're all giving tutorials today. I want to thank SAMC for being a wonderful host for this, especially Ilse Ibsen. She has answered so many of our emails, and she's really the one making this happen. And I also want to thank Sue McDonald, who's also looking after a lot of the details and just making it easy and comfortable for us to come and talk about math. All right, and thank you all for your attention. And there's 10 minutes for questions, and I have to remember to repeat your question.
So I didn't understand your points about the applications of Markov chain Monte Carlo. Maybe you were typing something of a particular type, because when I think of, say, like a simple random walk Metropolis Hastings,
Yeah.
I don't see what you're saying fitting with that. Am I?
Okay, so the question is, how does this actually work for random Metropolis Hastings? How would you use quasi-Monte Carlo? And so when you're in your random Metropolis MCMC, you're about to take another step. So you take a bunch of random variables to propose where to go, and you save one out to do accept reject. So maybe it takes you 10 to propose where to go and one more to accept reject. So you need 11 uniform numbers to make that decision. And then once you've made it, you need 11 more for the next one and 11 more after that. And what would not work would be to take an 11-dimensional QMC sequence and feed it to your MCMC. But what does work is to take a completely uniformly distributed sequence and feed it in. So you can take, instead of 11 IID uniforms, you can just take 11 numbers in the unit interval, and the algorithm will work. Is that?
I guess I don't understand why it would be either better or worse. It seems to me that because at each point, your acceptance rejection is so different. It would seem to me like it all get washed out anyway.
Well, it ends up. So with acceptance rejection, that's a discontinuity which will give you infinite Hardy-Krauss. So we find empirically that it works a little bit better. But we don't see a better rate for the acceptance rejection methods. We do see better rate for Gibbs.
So what if you separate it so the random variables in the proposal are drawn differently than the random variables drawn in the accept reject?
Yes, so the idea is to pay attention to whether the random variable is a proposal one or an accept reject one. Yeah, and I think you can improve. I think there might be strategies that would improve that. I think there's more to be gained by running Gibbs, though, because it has a lot more smoothness. So Metropolis, it worked okay, but we seem to see a better rate for Gibbs and not for Metropolis. Yes.
The first one is I'm quite new to this area, so forgive me if I'm asking silly questions. So the first one is, so you use Coxman inequality to estimate the error. So what if f is not derivative? Like, for example, f is like discontinuous or?
Oh, then we're out of luck. So the Kossel-Hofka will give you some assurance that the error is going to get small, and it can, if the function is smooth enough, And it'll give you assurance that the function is going to get small even faster than it would with Monte Carlo. But it won't help you say how small your error is, because it has a discrepancy which is pretty hard to compute, and a variation which is considerably harder to compute than the thing you're trying to do in the first place. So Cox-Mihalowska will not actually tell you how well you're doing for fixed n. However, if you do randomized quasi-Monte Carlo, that's the approach I like. You randomize it, say, 10 times, and if you see that you're getting the same answer to, say, 5 or 6 places each time, you can be pretty confident that that you've settled, that you've got a good number. But your point is well taken. If it's very easy for some function f to have infinite variation in Hardy-Krauss sense, so it's a motivational tool. But when it comes down to business, you have to do something else.
So the second question is, so what if the integral happens on the sphere, like not the cubes?
Oh, well, you should talk to Kinjal Basu, who's here. So there's a lot of, so this is something Kinjal and I have been working on for a couple of years. Like, what if it wasn't the cube? What if it was a triangle simplex, or the sphere, or a ball, or something else? And first thing you'd think of is you could just map your cube onto one of those spaces. And then the mapping, sometimes the mapping messes up has a transformation that messes up the smoothness you would like. So talk to me or Kinjal sometime during today or the week, and we can tell you more about it. Yeah, so if the function is infinitely differentiable, or let's say it's even better. Let's make it analytic, or let's make it even smoother than the usual analytic functions. Then you might try some Kriging methods with Gaussian kernels, what the probabilistic numerics people like to do, and then you can get exponentially fast convergence. In theory, and who knows. Right, so those methods, if you're converging exponentially, then maybe you don't mind that it's n cubed work with n points if you've got exponential convergence. Well, so it's clear, like what you said, is that it changes the problem if you have that amount of smoothness. And it'll give you a way better asymptote than you can get without that amount of smoothness. And then it's all a question of when can you actually attain that asymptote and when is it beyond your computer budget. Yeah, so it's going to be a pretty solid maybe, right? You'll find out when you do it.
session. It's my great pleasure to introduce Pierre Lecoyer. Pierre is on the faculty of the Computer Science and Operations Research Department at the University of Montreal. There he holds the chair, the Canada Research Chair in Stochastic Simulation and Optimization. And on the other side of the ocean, in France, he holds the INRIA International Chair at INRIA Rennes. Pierre is a fellow of INFORMS, the Institute for Operations Research and Management Science, and he has been the recipient of many of their prizes, in particular their Distinguished Service Award. So Pierre's research interests include random number generators, actually tons of research interests, but in particular random number generators, quasi-Monte Carlo methods, discrete event simulation. And in addition to numerous publications, Pierre has also developed a number of software libraries for random number generators and QMC points. Let's welcome Pierre.
So I guess you wonder what is this, huh? Art told you about next year QMC. Is going to be in Rennes, in Bretagne, in France. And so in Rennes, on Saturday morning every week, there is one of the nicest markets in the world, actually. There you can find, for example, scallops, les coquilles Saint-Jacques de Saint-Brieuc. And the fishermen come there, and you have them open, alive for you and so on. And this was on Saturday night, after the Saturday market in April this year in Rennes. So these are scallops. So so that you remember, that there is QMC next summer in Rennes. Right, that was my that was my publicity. Whoops, it's not the one I want to show now. All right. Whoops. What's happening here? Just a minute, I have a... Okay, I got it. So I'm going to talk about lattice rules. Well, first of all, I have to thank Samsi and Ilse and the people who co-organized this with me, but I did almost nothing. I just coming here to enjoy. I'm going to talk about lattice rule, mostly assuming that we want to do integration. So I just go through the basic notation first, and just to give you my notation. We assume that we want to estimate an integral like this. Oh, this is a bit weak. We want to estimate an integral over the s-dimensional unit hypercube. So Monte Carlo, well, you will generate independent copies of the random points in the unit hypercube. Actually, the idea that pretty much every integral can be put into this form, you can understand that by the fact that, when you do a simulation, you generate uniform random numbers. Sometimes the number you need is random, but nevertheless, when it's random and unbounded, you can take S equal to infinity. But this is how it works. Huh? Everything is a function of the random numbers, the uniform random numbers that you use at the bottom of your simulation. So you can write things that way, and I assume that. And with Monte Carlo, you can do independent sampling and compute confidence intervals. With quasi-Monte Carlo, you replace those independent points by a set of deterministic points that cover the space more evenly, as Art has explained. And you have some estimator Qn here, which is deterministic, and some error, which is also deterministic. And you would like to have a point set that is highly uniform or have low discrepancy with respect to the uniform distribution. And so there are many ways of measuring the discrepancy and to construct the points. There are mostly two most important classes that people use, lattice rules and digital nets. And I'm going to talk about lattice rules. And actually, some of them turn out to be digital net as well. Polynomial lattice rules. I'm going to talk about them a bit. Okay. So what is a lattice rule? So let's start with a very simple case, one dimension. In one dimension, you want to place points evenly distributed in the interval 0, 1, right? So what you can do is very simple. You can just take all the integer multiples of 1 over n modulo 1. So you get the red points here. And so if you take the average of your function at those points, this is equivalent to doing a Riemann sum. You can center the points in each interval. You get the midpoint rule. And you can show, well, if your function is smooth enough, you get an error of 1 over n squared with this. I don't know what's going on here. I think it's the connection here, yeah. Should be okay. Okay, so what about higher dimension? Well, you can start with a grid. That's a naive solution, maybe. You can also center the grid. It's kind of a multidimensional midpoint rule. But when the dimension increases, this thing becomes impractical. Art has already mentioned that. One idea which started with Koroboff, 1959, is to use a lattice. And so the definition of a lattice is as follows. What you do is you want an integration lattice. So you want your lattice to contain all the integer points. And so what you will do is you take a set of independent vectors over the real numbers, and you take all integer linear combination of those, and you choose them in a way that the lattice contain all the integer points. And for that, you must have that each coordinate of each vector must be a multiple of 1 over n if you have n points, and so on. So in practice, we normally use a lattice of rank 1, which means that all the points are an integer multiple of a single vector modulo 1. So the other vector in the basis are just doing the modulo 1 operation, basically. That's the idea. And to do that, you can specify, well, you first choose an n, the number of points, and then you specify a vector whose coordinates are all integers, and you divide this vector by n, so you get your v1, right? But you have to do it in in a special way. You cannot take any a and any n. That's pretty much how we define these things. So there are some special cases, like Koroboff was using a vector of this form, 1a squared, and so on. What is interesting here is you can get the next coordinate by taking the previous coordinate, you multiply by a modulo n, and it's just like doing a linear congruential generator. So you can generate as many coordinates as you want. You kind of have an infinite number of coordinates with that. And it's useful sometime in some implementation. You can project your lattice over a subset of coordinates, and it's also a lattice. And the lattice rules that we use, normally we would like them to be fully projection regular, which means that when you take the projection of the lattice and you intersect that with the unit cube, all the points are, remains distinct. In particular, each one-dimensional projection contains n point for every coordinate. And for a lattice rule of rank 1, it's very simple, because this is true if and only if each coefficient here has no, is relatively prime with n. And if n is prime already, then you already get that. So yeah. Okay, so here's an example of an integration lattice. So you can see that all the corners, the red points, belong to the lattice. And this one has n equal 101. The generating vector v1 is here. It's a lattice of rank 1. So the vector v2 is this unit vector here, which it's kind of used to do the modulo 1 operation. And so all the integer linear combination of those two red vectors are all the blue points, and it goes to infinity in every direction. So this is the lattice. Then you take the intersection with the unit square, and then you get a finite number of points, 101 points. And so you evaluate the function in 2 dimensions at this point. You take the average, and basically that's the lattice rule. Okay. Here's another example. This one has 1,021 points. The two generating vectors are v1 here, and the other one the same as before. The one before, I can change the 12 that we had here to 51. So what happened if I change 12 to 51? Well, what happened is my generating vector here is almost parallel to the vertical, and it goes about halfway to between 0 and 1, right? It's about 1/2. So this means that the next step, if you take 2 times v1, you're going to get very close to 1. Actually, you get right here, because you do the modulo 1 operation. And so basically what you do is you jump from here, 1/2, back, 1/2, back, 1/2, and all the points turn out to be on 2 lines like this, which is very bad. Okay? So this happens with bad choices of multipliers. You can get this structure. Okay? And so maybe I'm skipping ahead a little bit. So one way to measure the quality of a lattice like this could be to compute the distance between the lines, or in higher dimension, the distance between hyperplanes. And this is used for random number generators. This has been the traditional measure of quality. This is called the spectral test in that context. And so here, the distance between the lines is quite small. You know, all the space is packed pretty much evenly. And here it's, it's pretty bad. You have only 2 lines. So a large distance, and it's not so good. So the distance between the lines is actually the inverse of the length of the shortest vector in the dual lattice. And so it's computable, and there are some very fast algorithms actually to compute that when the dimension is not too large. You can have a very large number of points. You can have maybe 2 to the power 1,000 points, and you can still compute it very, very quickly, okay? Which is not the case with the measure we will use with lattice rule like P alpha or so. But when the dimension increase, then you know it gets much harder. Okay. Bon. You can also have embedded lattice, a sequence of lattice that are embedded within each other. So the next lattice is a superset of the previous one. And typically for those type of lattice, usually we will take the number of points in each lattice will be a power of 2. And then the next lattice will be basically the next power of 2. Huh? So you have, for lattice number xi, we'll have 2 to the power xi points. That's the simplest way to do it. And you can have, in that case, you can take the generating vector multiplied by n here. You take, it's an integer vector. So you will take it so that this vector modulo the previous modulus will be the previous multiplier like this. So yeah. So basically, and there are tools to construct those embedded lattices as well. Yeah, I'm going to talk about a software tool to build lattices later on. It's called Lattice Builder. And Lattice Builder can contain all kinds of tools to build, for example, lattices of this kind and so on. Well, the traditional measure of measuring the error and the quality of the lattice in quasi-Monte Carlo, lattice rule and so on, is based on Fourier expansion. So suppose your integrand f has this Fourier expansion here with Fourier coefficients f hat of h. And suppose that this series converge absolutely. So in that case, the error is exactly this sum. There is an expression for the error. It's the sum of Fourier coefficients for the vector h that are in the dual lattice. The dual lattice is defined as the set of vector h for which the scalar product modulo 1 is equal to 0. So scalar product is an integer. So you get an expression for the error. The problem is, of course, we don't, in practice, we don't know those guys, huh? But it gives a way to study what happens. And it is also known that if the function f has square integrable mixed partial derivatives up to order alpha over 2, where alpha is some even integer, for example, with alpha equal 2, here we want partial derivative of order 1. And also, if the periodic continuation of the derivative up to order alpha over 2 minus 1 is continuous. So for alpha equal 2, you only need the function to be continuous across the boundaries. Okay, so so it means that basically if you take evaluate the function with one coordinate equal to 0, you replace it by 1, or when it converts to 1, the two values are equal. Right, that's the meaning. In that case, the Fourier coefficient here converge like this. You know, you have this bound with some hidden constant, and so that's one thing. So you know the rate of convergence of the Fourier coefficients, or an upper bound on it. And you also know that so the error will be bounded by this sum, basically, with some constant in front that you don't know, but it's a constant as a function of n. And so you know that this sum also, well, there is a lattice, at least one, for each n, for which you have this measure converging like n to the minus alpha over 2 plus epsilon. Okay, so roughly, if alpha equal 2, you get almost order of 1 over n convergence. If alpha equal 4, you get order of n to the minus 2 for the error, not the variance. So this is the worst case error. So this is much better than Monte Carlo. Okay, all of that in theory, of course. And there is another thing. I'll say there is a lattice, but when n is very large and the dimension is very large, there are so many possibilities for the vector A for the lattice, how are you going to find this vector? Okay, are you going to search to try them all and compute the measure and find the best one? Well, there are some results that also that say that you don't have to look at all of them to find one that converges at this rate. There is a method that was introduced, I think, at the beginning by Jan and his colleagues, called the component by component construction, where what you do is you start with the first coordinate, and then to find the next coordinate of your vector A, you choose the best value of the next coordinate, okay, the value that will minimize some figure of merit in 2 dimensions. And then you go on and you go one coordinate at a time, and each time you find the best coordinate that you can for this particular dimension. And so you have much fewer possibilities to look at, right? And it is guaranteed that if you do that, you're going to find a good lattice in the end. Okay? Maybe not the best of all, but you're going to find a good one. And you can still get this order with that. So all of this is very nice, except that in practice, when S increase, you know, there are a lot of problems with this bound because it's, well, the constant in front gets bigger, and so the bound is not very useful in that case. And but there are a lot of generalization of this type of construction in inequality, where you can put weights on the different h. You can put larger weights to the h that are smaller. And the idea is that this thing will work when the Fourier coefficients for which h is smaller are more important than the ones for which h is very large. So that's roughly the idea. And so basically, if you assume some convergence in the Fourier coefficient, faster convergence of the Fourier coefficient when h increase, then you can still have something that works here. And so I'm going to come back to this. You know, it's vague at this point. I'm going to come back with the weights a little bit later when I look at the variance. Yeah, I think I have to move a bit faster. So let's talk about now randomized quasi-Monte Carlo. So the idea is that with deterministic points, it's very hard to estimate the error. Okay, we have some bounds that are theoretical, but we cannot compute them. So how can we estimate the error? Well, we can do that as follows. What we can do is to randomize the points, the QMC points, in a way that for each point, the randomized point will have the uniform distribution over the unit cube. So for each point, you have an unbiased estimator of your integral, and the average is also an unbiased estimator. And the whole point set remains a low discrepancy point set. And so then you have an unbiased estimator. And the variance, well, if you do that, you know, for the point set to remain a low discrepancy point set, it means that there is some correlation between the points, right? And so the variance expression in the end will be the variance of the average will be the variance of each f of u over n. So, and if the points were independent, you will have only this part. You will not have the green part. But because of the dependence, you get the green part, and you want this green part to be negative as possible. So this is a way of seeing things intuitively. Okay, you want to induce some negative dependence among the points. And QMC is not the only place where we're trying to do this. Anesthetic variates, that's exactly what we do. Latin hypercube sampling, this is what we try to do as well. And stratification, this is also what we want to try to do, right? This, the same general idea. Okay. For the lattice, one way to do this, what I just said, you generate a single point uniformly in the unit cube. You add it to all the points. So you know, the points we had before become, whoops, it goes too fast. The point we had before becomes those points. They are shifted randomly. And then you do modulo 1. So you bring back the points inside the cube, and these are the randomly shift points. Okay? Very simple. So yeah, here's another example where you can, I have numbered the points so you can see where the points are ending up. So you have this U here that you had to all the points. So 0 becomes here, and I don't know, 5 here. You had this shift modulo 1, it gets here, and so on, right? So yeah. Actually, instead of generating the uniform point U in the whole hypercube, you can generate it in one of the polytope generated by the basis vectors. For example, you can generate the random shift inside this figure here randomly, and you had the random shift like that, and it's equivalent. Okay, you can show that it's the same thing. And actually, it leads to the idea that one might generate a random shift like this if you partition your whole hypercube into a polytope like this, you can generate the random shift independently across the different polytope, and that becomes a way of doing stratification. It's a stratification thing. It's not necessarily better. Huh? You know, you have more independence. In some case, it will be better than the randomly shift lattice rule. In some case, it will be worse. It depends on the function. Yeah. And maybe, yeah, another problem is, well, this polytope here, well, it's like this, but when you look at all the polytope, one of the polytope will be the green area, which is split into several places. So if your function is periodic, it doesn't matter much, but if your function is not periodic, you know, you generate a random point in this green area. It's not hard to do, but it seems strange. But you can do that. What is a bit less obvious is that you can also generate points into those different type of areas. You can generate your random point into this one or into this one, basically, or the green one here, or the green one here. And basically, the idea is that if you have a partition of your unit hypercube into areas of similar shape that are just shifts of each other, you can generate your random shift in one of them, and it's the same as generating everywhere. Okay, so you can do that, but you can also do it independently in that case, and it becomes stratification. So here's the general proposition that says, I'm going to go faster with that. So here's, yeah, I have some interesting figures. When you have, what I did here, I took a function, this function in 2 dimensions, and I have those black points, 8 points, and I apply QMC, right? And so the error that I get depends on the random uniform that I generate right? So I have a function of u, and this is this function of u. So when well, in the yellow area, the error is pretty small, but in the red area, you have a large positive error. In the blue area, you have a large negative error, and you have patterns of how the error behave as a function of where you put your random uniform. So you have this pattern. For this function, you get this pattern here. And if you, instead of multiplying, you add a different function, you get this pattern for the error. And here is a nicer one. You get a more complicated function. And the integration error here is, in most of the area, it's yellow, so it's not very close to 0, actually, in most places. But you have some deep holes here in blue, where you have a negative error, and you have some peaks around the points where you have a lot of positive error. So if your uniform is very far, well, if your uniform is midway between 2 points like this, you have a large error. If it's very close, you have a large error. But if your random, depending on your random shift, yeah. But it's a nice picture. Okay. What happened if you do a randomly shift lattice? And what happened with the variance? Because you can say, I have an unbiased estimator, so maybe the right way to measure things is the variance, right? So, well, it turns out that for function f with these Fourier coefficients, with a randomly shift lattice rule, the variance is the sum of the square Fourier coefficient over the vectors of the dual lattice. And this does, for this to hold, you don't need the series to be absolutely convergent. Okay, the conditions are weaker than for the error itself. Okay, you only need the variance to be finite, that's all. So the function can be discontinuous, whatever. Yeah. So when you look at this, well, you might think, well, the optimal lattice for a given function would be the lattice that minimizes this thing, huh? But it depends on the function, of course, right? Okay, whoops, it goes, okay. So this is my expression of the variance. And as we saw earlier, if the function is square integrable and so on, you know, you have enough smoothness, you have this type of bound on the Fourier coefficient. On the square Fourier coefficient, you just square the thing that we had before. And we have a measure that is squaring, you know, well, we just take alpha instead of alpha over 2 here, and we get this convergence rate for the variance. And this happens for the worst case function for this measure, which reach exactly this error, is the function for which the Fourier coefficients are exactly like this. Okay? And this worst case function that I just wrote, you can write it differently. Actually, this is this function. You can write it in terms of Bernoulli polynomials in case alpha is an even integer. So for alpha equal 2 or alpha equal 4, for example, you can write it like this. And yeah, so it defines, so this, with this, yeah, my thing is jumping too fast. So this means that the P alpha that we have here in case alpha is an even integer, we have an expression that is, instead of having an infinite number of terms, as in this sum, which we cannot really compute, here we have, when we replace with this, we have a finite number of terms, and we can compute things. Actually, we can compute pretty efficiently. I'm not going into the details of that, but yeah. However, this worst-case function is not necessarily representative of what happens in application. This is the worst case. Okay? Sometimes things will go much better, and the Fourier coefficients, actually, we don't know exactly. There is a hidden factor in the big O, a hidden constant, and so on. So there are a lot of other problems that are hidden under the carpet here. Okay. So this can be generalized. The P alpha that we had before, we can put additional weights here that multiply the value here for each Fourier coefficient, basically. And so, but how do we choose those weights? Well, the optimal weights, in theory, we know what they should be, but we don't really know because we don't know these guys. Right? So what people do usually is to reduce the number of weights. So you kind of bundle up things together. And instead of having a weight for each h in the Fourier expansion, you put a weight on each subset of coordinates. So what you do is you put all the h that have the same non-zero coordinates together, and they correspond to the subset of non-zero coordinate u here. And this basically corresponds to the ANOVA decomposition. You write your function as a sum of function fu, where u is a subset of coordinates, so you have a constant of sum of one-dimensional function plus a sum of two-dimensional function, and so on. And for each term here, you put basically intuitively as much variance as you can, as much variation as you can into the low-dimensional function that you have. And the way they are defined is like this here, but yeah, intuitively that's the idea. You want to capture the variance in the lower dimensional subset. And if you decompose your function like this, the variance decompose in exactly the same way, and sigma u square is actually the variance of fu that comes into the sum here. Okay, so it is very nice, and so. Well, in practice, you will say, oh, yeah, but how can we know those sigma u square? Well, in practice, sometimes you can have some rough estimates of them. You can do some pilot runs for some problem. I'm going to show you an example where you can get some rough idea of what are the most important components here. And for them, you put larger weights. Basically, that's the idea. And so to do that, you can define P alpha that we had before with weights that depend on u, right? And so you would get this P alpha where the weight here depend on u. And this is the version of P alpha where alpha is an even integer. This thing you can compute. And actually, with this P alpha, if you view it as a discrepancy, there is a corresponding variation, square variation here, and you have a Koxma-Lafka type inequality here that gives you a bound on the variance. So the theory goes on like that. Actually, this can be generalized even further because instead of Cauchy-Schwarz here, you know, you can use Holder inequality. You can basically put every term in this sum here, you can put this to a power p and the other one to a power q, and where 1 over p plus 1 over q equal 1. So you get, you know, a more general version of this. I'm not going into that, but you can generalize. I'm not sure how useful it is, you know, well, in practice I use two. Normally I use this one. Okay, so this weighted P alpha, again, I wrote it again. And the worst case function here, you can write it explicitly with those weights. And if you take this function and you compute the ANOVA decomposition for this function, this worst case function, this is what you get. You can obtain the sigma u square exactly for this case. It depends on the weights, of course, but those things you know, right? And so from that, what you can say, you say, okay, let us assume that I want to choose my weight for the worst case function, this function, okay? What are the optimal weight I should have in my P alpha for if my integrand was exactly this function? So this you can do, because you have a sigma square as a function of this. And so what you, for example, for alpha equal 2, you can compute this, and what you get is gamma u will be this quantity. Well, basically it will be something like this, 0.3 to the power the cardinality of the subset, sigma u square. So, so if you know sigma u square, you can compute basically the optimal weight, right, as a function of sigma u square. That is true for this function, for the worst case function. So, and then you can use this in a heuristic way. You can go, you know, what you can do is you can have a rough estimate of the ANOVA variance component. And from those rough estimate, well, you can choose the weights. Okay, this is somewhat heuristic because your integrand is not really the worst case function. But I mean, otherwise, what can you do? Yeah. So what is important to retain here is that suppose you have estimates of your ANOVA components. Those are not the weights. Those should not be the weights. The weight should decrease exponentially also with the cardinality of u, you know, even for constant sigma square. Okay. So more heuristic for choosing the weights. When the dimension is large, you have a lot of subsets to consider, and you cannot in practice, well, I suppose the dimension is 20, you know, you're not going to have 2 to the power 20 different weights. It's too much. And or maybe some you assume to be 0 or something, but you have to do something else. And there are different ways of handling this thing. For example, you can assume that you have a weight sigma j for coordinate j for each j, and the gamma u will be the product of those gamma j over the different coordinates that are in u. Okay, that's one way that has been proposed a long time ago. Another way is to assume that the weight depends only on the cardinality of u. So all the subset of cardinality 3 will have the same weight, for example. And you can have a combination of this with product weight and order dependent weight together, for example, and so on. Okay, there are different heuristics like that you can have. What if you want to have alpha different than 2 or 4 or 6, or not an even integer? Alpha equal 2, you have smooth function. Alpha equal 4, it's even smoother. Maybe you want less smooth function. Alpha equal 1. Alpha equal 1, you don't have a formula for like P alpha that you can compute. You still have an infinite sum. So, but there is another criterion that truncate the sum, basically. Basically, you truncate the sum to the vector h that are rather small. You go inside some box, and all of that is in the book of Harald, Niederreiter. And you can, it's possible to bound the P alpha in terms of this truncated measure. And this one you can compute, right? Yeah. So that's another thing. There are figure of merit based on the spectral test. I will skip that. How can we search for good parameters? Well, you can say I'm going to stick to Koroboff lattice, so the vector will be of that form. And then I have to search only for A, okay? So I reduce the space. It's much easier to search, but then you have less flexibility, and the best one might not be as good. You can just try random values of A. So here. So when n is very large, you may just try some random values of A, and you take the best. You may say, well, if I have a lattice of rank 1, in general, you can say, I'm going to try all vector, exhaustive search. It's but when the dimension is large, it takes too much time. You cannot do that. You can just try random search, vectors A at random. But there are better methods. The component by component construction that I mentioned earlier, you can say, okay, I'm going to start the first component will be 1. I can do that. Then I take, given given the previous component, let's say, given for G so suppose that A1 to AJ minus 1 are already chosen. Well, I fix them, and I try the next one. I try all possible values that are admissible. So if I impose that the GCD with n is 1, then I restrict myself to those, and so on. And I pick the value that minimizes the discrepancy. The discrepancy can be the P alpha, but it can also be the other measure that we have seen. And yeah. And actually, there is a way to do this using fast Fourier transform. You check all the z at the same time, basically, and this is extremely efficient, very, very fast. Yeah. It's easier to do this when n is a prime or a power of a prime than when n is general, but it can be used more generally as well. You can do, if you don't want to do all the component by component construction, for example, if n is very large and you say, I don't have time to look at everything, at all the z at each step, then you can just try some z randomly at each step also. Okay? And typically this thing does almost as good. Sometimes it does better than the other one. But when n is prime, it's not really much faster. Huh? It's not, unless you take just a few. But you take just r very, very small. But if you, I don't know, you try 100 or 1,000 of them, you can do the fast CBC, and it will be, you will look at all of them in the same time. Okay, so what else? Embedded lattice. I'm going to skip this. Available software tools. So there are some software tools to construct lattices. There are also software tools to analyze. Once you have the parameters, you can generate the points in your simulation, and those tools should be in simulation software. So I have a simulation software library in Java, which is called SSJ, that contains all these point sets. You give the parameters and it generates the points. For example, for a digital net, you give the generating matrices in a file, for example, in some format, and it will generate the point. But you can also have some matrices that are pre-compute in the software. You have both. To find points, there is a software called Lattice Builder, which is available on GitHub, where you can say, okay, I want a lattice rule with a given number of points. Here is the interface. There is a web interface for it, but you can also have it with a command line. You have a command with a lot of options, and it gives you at the end a lattice, or it can put the parameters in a file. So here is an example where I say, okay, the number of points I want is 2 to the power 10, so it's 1024. Or I can change it. I can say, okay, no, 2 to the 11th, let's say, okay, for example. I can have a simple lattice, or I can have an embedded lattice. So embedded lattice means that it will do a lattice with 2 points, 4 points, 8 points, or whatever, all the powers of 2, until the highest value that you want, which is this one here, actually, 2 to the 11. And so here the dimension is 3, I can put 5, whatever. I can have, for when you want embedded lattice, for each size, you have a figure of merit, but you have to combine that. So how do? You have some normalization of the figure of merit, and you do a sum, or you do worst case. So you have different choice of ways of combining the figure of merit here, which is explained in the guide and paper. Figure of merit can be P alpha with weights, can be R alpha, can be based on the spectral test. P alpha, you have to choose alpha, of course. Evaluation method can be, for P alpha, okay. So there is only one evaluation method for that case. It will take the fastest one. So I can specify the weights for each. I can specify the weight for each projection. I can specify the weight for a product weight, weights per coordinate, all those methods are available. So I can do random search. I can do fast CBC, for example. Random CBC. Where is fast CBC? CBC. Whatever. And then I run the thing, and it will give me some. It will give me some lattice. And when I'm finished, I have the generating vector here in 5 dimensions. The figure of merit, the number of points, and so on. And now, okay, I want to have a code to generate my points, right? I want the code, let's say, in Python. So I click Python, here's the code, right? Fred wants the code in MATLAB, I know. So we have the code in MATLAB. So it produces the code like this. So It's interesting. So right now, we have finished implementing the polynomial lattice rule. So at the beginning, you can choose ordinary lattice rule or polynomial, and then you will have different options. Yeah, so polynomial lattice rule, I got the first results only this morning. So it's running, but it's not yet online. Okay, so I'm going to skip this. I'm going to skip a number of things. I have some example. Maybe I have 5 minutes, huh? Huh? 4? Okay. So I'm going to skip the example. I have examples where I show ANOVA variance. Basically, okay, I'm going to shrink this in a very short. Basically, you have some problems where you have an estimator, and the estimator is your function. So here, in this example, I have an estimator where I have a network, and I want to estimate, let's say, the probability that the longest path in the network is larger than x, right? So when I do ordinary Monte Carlo, I will take I simulate the network. If the longest path is larger than x, I count 1, otherwise I count 0, right? So each value will be 0 or 1. And so this is, well, this is an indicator function. It's not very smooth, right? And so one way of making the function smoother in this particular case is taking the conditional expectation. So what you do is you generate only certain length. The lengths are random. And conditional on the one you generate, you compute the probability, the conditional expectation of the indicator, which is the conditional probability that the longest path will be larger than x, given what you have. Okay? And you choose the one that you hide. The one that I will hide here are the light blue ones. They form a cut in the network. And with that, there is a very efficient way, very easy way to compute the conditional probability. But this conditional probability, it's smoother. Now it's continuous, right? So it helps. And it's not only continuous, it's also has fewer dimension because you generate fewer random variables. So you can reduce the dimension of your integrand. You can make it smoother by different tricks. And, well, Art talk about Brownian bridge techniques. But you know, conditional expectation is another one. And there are many other ways of doing that. Yeah, and you can see that when you do that, the proportion of variance that are eaten up by the one-dimensional projection, it's in blue. When you do conditional Monte Carlo, it increases a lot. And the pink one is the one taken by the two-dimensional projection. So, you know, one and two-dimensional projection will have pretty much almost all of the variance here with QMC, whereas without, you know, you need higher dimensional, you have higher dimensional ANOVA components that are counting a lot more. And also, when you look at the convergence of the variance, without the conditional expectation, you have a gain in the variance, but the slope is about the same as Monte Carlo. Okay, this is 1 over n. This one is 1 over n here and 1 over n squared. So, yeah, with QMC, it's not very good. But if you do the conditional Monte Carlo together, it's better. And it seems to, you know, when you go further, the slope improves. Yeah. Yeah. Okay, we're finishing. Okay. So just one last thing. When you do randomized quasi-Monte Carlo, you have an estimate of the variance. And you may think that you can use that to compute a confidence interval using a normal distribution, right? Okay, here is an example, well, where we made an experiment with this example where you have a Monte Carlo estimator. We replicated 10,000 times the estimator that use 8,000 approximately points, right? With Monte Carlo, we get something that is very close to normal, and you compute a confidence. We know it's the central limit theorem. But with RQMC, when you use this number of points, here's what you get for the average. This is the distribution of the average at the bottom with RQMC. So it's not a normal distribution. So what I suggest is when you do several random shifts, several randomization of your points, you should plot a histogram. Okay, you do 20 times, 10 times, whatever, plot a histogram, or put all the values if you do only 10 times. You will see, you will have an idea. If you do 100 random shift, then you can do a histogram, and it gives you a better visual idea of what goes on. Okay, so I think I have to stop here. I have more stuff, but.
Thank you very much.
No. I learned about lattice rule by reading the book of Jan Sloan and then the papers by Fred Kernel. And so they're both here today. And Fred was in Hong Kong at the time. And but for many years now, he's been at Illinois Institute of Technology. And he's still working, very, very active in this area. And this afternoon, I think he's going to talk about how you you measure the error, or when you have quasi-Monte Carlo point sets in an adaptive way. So that's going to be quite interesting, hopefully useful.
Thank you. So I've had the pleasure to be a part of this community since the first Monte Carlo, quasi-Monte Carlo conference in 1994 in Las Vegas. And there was a 0th one in Alaska that I didn't get to. But it's a great community, and as I was listening to the first 2 tutorials, I felt like, oh, there is so much more that Art and Pierre could say if they only had time, because there's so much in this field. And for some of us like me, it's taken me a long time to learn it, what I do know. This is a picture from the south end of our campus looking down into Chicago. If you come and visit me, I'll take you to the president's office and knock on his door, and I say, we'll have a distinguished visitor who would like to see this view, and we'll show it to you. But it's a very pretty place where Illinois Tech is. I'd like to start off with some applications, and there are many applications, but these are a few that I'm familiar with, and I will come back to and do some numerical experiments. So you want to know what is the fair price of an option. And there are market prices, but you may be trying to understand whether that fits what your model of what you think would happen. And so the option price depends on a stock or a basket of stocks and what they do cannot be predicted. It's not really a mechanical process, but you can model it randomly. And so let's think of F as the payoff, discounted because at some future time, dollars aren't worth quite as much, although with the interest rate today, discounting is not a big factor. And this X is all of the random market forces. And so the fair price is the mean, or we'll call it mu, of the payoff. And I'm going to use mu for integral. As you saw in the earlier, mu was often used for that. And although it may not always look like a mean, we're going to think of it as a mean because we're going to use Monte Carlo methods. Another example is you have a random variable x, and you want to know the probability it lies in some subspace of the sample space. So again, you can write that as an integral. Here it's not so clear what the probability density or the measure, nu here is a probability measure, should be. But you'll have to make that determination, and then again, we think of it as some mu, and G is given. Up here, F is given by your model. And then I'm also going to look at a problem that's a little different, briefly at the end of my talk. It is the function of 2 integrals, in this case a quotient. A Bayesian inference problem is some integral, some function integrated against the unnormalized posterior density, and then you have to divide by another integral, which is the normalizing constant. And so here we have not one, but at least 2 integrals. Clementine is going to talk to us about Sobel sensitivity indices, and there again we have several integrals. So we also like to know what you can do when you have several integrals. And so these are examples of what I'd like to call a general problem. I have some function that I may not know a whole lot about, but I know how to evaluate. So if I give you an x, give the black box an x, I get back an f of x. My problem can be written as the integral of this function against some known probability measure, often continuous, but doesn't have to be. And because this is too hard to do analytically, I'm going to estimate it by the weighted sum of the function at n different values of x. So we'll assume that f is that when you put in x, you always get back the same f. If there was noise, that would be an interesting problem, but we're not going to consider that case. The weights here will depend on x. They could depend on other things. They're often just 1 over n, but I'm going to keep it a little general because it might be useful. And then one thing I'd like to note is that we can also think of this sum as an integral of f integrated against a sampling measure. So the idea is, if you have an f, how would you choose the sampling measure? How would you choose the x's? How would you choose the w's to make your sum, your approximate integral, as close as you can to the real integral? And how small is this? Now, Pierre said I'm going to talk about how to do it adaptively. Actually, that's what I would love to talk about, because that's my present research interest. But I'll only talk about that towards the end, because as a tutorial, I sort of wanted to get through some of the more basic, which is non-adaptive, which is touching on some of what's been said before, but I think the repetition may be helpful. Also something different than what's said before. And I'll talk about, so how do you actually determine that n is large enough at the end of my talk. But first we'll just try to see how can we characterize this error in a way that's helpful. And so first we do is we write this error as the integral of f versus the difference of two measures. So we have two probability measures. Typically, nu hat doesn't have to be a probability measure, but it often is. And the difference will not be, so this is some signed measure. And so you can see that if f gets big in some sense, the error will get big. If this difference gets big in some sense, then the error will get big. But there's also then this idea of if they are aligned sort of in parallel in some sense, that's bad. If they're orthogonal in some sense, so one is big when the other is small, then that might be okay. And so what we find in practice when we try applications is we get an error. We observe an error. We may not actually know what it is, but we can see it. And then we try to do an analysis, and we try to give a rigorous argument of what we think it should be. And our rigorous argument may or may not line up with what we observe, because there are some assumptions that we may not know for sure if they hold, but we hope they do. And when our analysis doesn't line up with reality, then that's an interesting problem, and we try to go back and say, well, what could we do about our analysis? Maybe we need to do something different. And I'll show you a couple of examples of that. Okay, we're focusing on quasi-Monte Carlo methods. And so these x's, which may be random, may be deterministic, but they're more carefully than IID. So the ID, independently distributed, they're supposed to look like the distribution that we're trying to mimic, but definitely not independent. They have to be dependent, and this is what gives us better convergence. So let me spend a little bit of time on this idea of what you heard earlier referred to as a Cox-Milovka inequality. I think there was some mention of reproducing kernel Hilbert spaces, but I'm going to spend a lot of time in this section RKHS because I really like it. It was sort of my first foray into quasi-Monte Carlo, and I keep coming back to this tool because it's really nice. And if you haven't seen it before, I hope you'll appreciate it. And if you have, hopefully it'll be like a movie that you've enjoyed watching, 10, 20 times, and would enjoy watching again. So we have a Hilbert space. Our integrand, the function we're integrating, is going to lie in a Hilbert space, which means that it's a vector space and it has an inner product, and it's complete. So these are the important things. And we're going to have a kernel called a reproducing kernel, whose domain is 2 copies of the domain of the functions. And this kernel has 2 important properties. If we fix one of the arguments, then it's a function of the other one, and that has to lie in the Hilbert space. It has to have the smoothness properties or the periodicity properties or whatever. And then the reproducing part means that if I take this kernel and I fix one of its arguments, and I should say that it's symmetric in the argument, so kxt and ktx are the same. And I take the inner product in the Hilbert space with some function f, then I get back the function value at that t. So this is why we call it a reproducing kernel. It reproduces function values. And why this is interesting to us is because unlike simple Monte Carlo, where function values may not even exist for some of the x's, for this kind of analysis, we need function values to exist. So functions in L2, that's not strong enough. This Hilbert space has to be smaller, say, than L2. And then if we have this kernel, and there are many choices, and each choice corresponds to a different Hilbert space, then here's the argument in about 2 lines of equations, 4 lines of words, that gives us an error representation, or in some sense an error bound. So, because it's a Hilbert space, and because we know that this error, so the true integral minus the approximate integral, is linear in the function, the integrand, and it is also bounded or continuous. So we assume that the Hilbert space is such that integration is a bounded linear operator. There is another element of the Hilbert space called the representator. We'll call it eta sub error, whose inner product with f gives you this linear functional. That's the Riesz representation theorem. So the Riesz representation theorem tells you it exists, but it doesn't tell you how to find it. But if we have a reproducing kernel, then we know how to find it, because we do this trick. And it's 2 equal signs, but I think it's really nice, okay? So the representer for error, evaluated at some point t in the domain, by the property of reproducing kernel, is equal to the reproducing kernel inner product with the representer. Now you say, aha, but this is also the cubature error for the reproducing kernel, where I fix t and it's a function of this first argument. And so just whatever I did over here, I apply it to the kernel. But now this kernel you've picked to be something that you know how to integrate, and then the sampling measure just is a sum. Okay? So you choose it so this integral can be done analytically. And I'll show you an example in just a minute. I am, in just a minute. That's what I said. In just a minute. Okay. There it is, okay? Next slide. But, okay, you look, here's an example, then I'll go back and finish my argument, okay? Maybe you'll like this better. Nu is the uniform measure on the unit cube. Nu hat is just the uniform on the discrete set. Okay? This is a kernel. Where did this come from? Well, people need to match the kernel up with the definition of the Hilbert space, and that is an art. But there are many examples. In the book by Berlinet and Thomas Agnon, there's several. So this is the definition of the norm. And the inner product would just be an L2 inner product, but here's what it depends on. Okay. I have this symbol, DUF, which means, let's suppose that U is the set 5 and 8. So coordinate 5 and coordinate 8. So I will take the first derivative of f with respect to 5 and with respect to 8. And then every other coordinate, I will set the value of x equal to 1. This is the anchor point for this definition of the kernel. So x1 equals 1, x2 equals 1, x3 equals 1, x4 equals 1, x6, 7, 9, 10, all equal 1. Now this is a function of x5 and x8. I take its L2 norm, and I do that for all other u that are subsets of 1 to 10. And that is the norm of my function with this kernel. And it appears in this paper if you'd like to see details. But there are many others. I'm trying to choose a simple one. Well, if you want dimension 1, this is just 2 minus max xt. And this is just the f of 1 plus the derivative of f with respect to x. And you take the L2 norm of those two things, that vector, and that's your norm. Does that help? Okay. And this is what the kernel looks like in one dimension. Here's t, here's x, and I've drawn this black line at t set equal to 0.3. So that's a tint. This 1 to d is MATLAB notation, meaning the set 1 up to d. The bar is the complementary set. And this is the discrepancy, which comes from the slide above, so I'll go back to that. Yes, I cannot think of a simpler example in d dimensions. So think d equals 1 if it'll help. Maybe while we're catching our breath on this slide, I wanted to give tips to all the new people. If you're going to write a paper in this field, you need to remember a couple things. When you use a subset of the coordinate indices, it must be fractor u, otherwise people will not understand your paper. This is just our convention. My tongue is in my cheek, but okay. There are people in the d is dimension camp and s is dimension camp, so you can use either one, but please do not use n for dimension, because we like to use n for a number of observations. And later I'm going to get to weights, which you've seen in Art's talk and you've seen in Pierre's talk, and they always must be gamma. Please do not choose another letter. I'm just trying to help you get your paper through the referee process without the referee saying, I don't understand this paper. So if you remember those 3 rules, D or S, you have your choice, fractor u, and gammas for the weights, then your paper stands a good chance of being understood, at least at the basic level, by the referees. Okay, so let me go back. So we have here an explicit expression. I'm assuming I can do the integral of k, which I'll choose that is the next one I do. And now I'm going to look at how I can think of this error. So this error is, as we said, the inner product of the representer with f. And now I'm going to use Cauchy-Schwarz. Except instead of having a less than or equal to and taking the absolute value, I'm going to keep this cosine term. The cosine has to be between plus or minus 1. I'd like to keep it now. This is something newly developed after I talked to Charlie Meng a year or so ago. But you can ignore it and just look at these last 2 terms. So basically, discrepancy, and I'm calling it DSC, or it could be DISC because it's the discrepancy, and you've heard about discrepancy. This is one example of the discrepancy, and it is just the norm of the representer. And this is the norm of the integrand. So we have broken up the error into something that only depends on how good is your sample in some sense, and how bad, or how, we said how good, but actually we should say how bad is the sample, how big is the discrepancy, and how bad is the function. And then the discrepancy squared is just the inner product of the representer with itself. And so we take this representer and we apply again the linear functional. So we take another integral with respect to the difference of the two measures, the true measure defining the integral and the sampling measure. And we now have 3 terms. We have 4 terms, but 2 of them are the same. And so this is an integral, easy to do if you've chosen the kernel correctly. This is the sum of a function that's integrated once. And then this is just a double sum. And sometimes we like to think of it as this is a scalar. This is a dot product of the weights with this vector k, which is the integral kx sub I going from 1 to n. And then this is a quadratic term. And the matrix k just has elements k of xi, xj. So one thing you might think is, if I wanted to choose the best weights, how would I do it? Well, the best weights would be chosen by taking the inverse of this matrix times this function k. And that's easy to write down. But if n is 1,000,000, you don't want to do perhaps n squared operations. So actually, a lot of things we can do if we don't mind doing n squared, n cubed. And some of the things I'll talk about, n squared and n cubed is cheap because n is small. But in a lot of cases, n is huge. And so we only want to do things that are order n, if we can. And a lot of times we will just choose the weights 1 over n anyways, even though it's not optimal. So the example that I showed before, here's the discrepancy. The integral is just 4/3. So you'll notice that this kernel is a product form. And product kernels are usually easier to do. People in the Krieging or the reproducing kernel literature, especially people that deal in spatial dimensions of 2 or 3, they're thinking they want to be isotropic. They like to have kernels that depend on the distance. But unless you're e to the something, that's not going to be product form. We like kernels in the QMC community that are product form because they're easy for us to deal with. Maybe there's other good reasons, but that's a big one. So let me tell you, this one has a geometric representation too, and Art referred to this, but mine's a little different because his was an L infinity discrepancy, mine's an L2 discrepancy. But this can shown to be the following. So here's my coordinate 5, coordinate 8. Coordinate 5 is 0.6, coordinate 8 is 0.4. This box has area 0.24. So measured against the uniform measure, it's 0.24. Measured against our sampling measure, it's 1, 2, 3, 4, 5, 6, 7 points out of 32. So it's 7 over 32. And 7 over 32 isn't quite 0.24. We would like it to be as close as possible, but it's this thing, the difference is 0.02, sorry. So we look at this for all possible x, not just 0.6, 0.4, for all possible U subsets, and we take L2 norms. And the square of that is the square of the discrepancy, and that's a geometric interpretation. So some discrepancies that you'll see in the literature have these geometric interpretations, and that's nice. But they also have cubature error interpretations. So let me review where we are. The error we showed was the cosine term times the discrepancy, which is the norm of the representer of the error, times the norm of f. In this case, because we have chosen nu hat to be uniform, constants are integrated exactly, so we can subtract off f of 1. This will become smaller because f of 1 was one of the terms in the norm of f, and we can write the error this way. So sometimes you don't have to just deal with norm of f. You can take f minus a suitable constant. And what do we know? We know that it requires order dn squared operations to evaluate because there's a d product here and then there's a double sum. We know that if we take Monte Carlo points, on average, it's into the -1/2. If we take digital nets, it's into the -1 plus a little bit. Those are the log terms. And it can't be any better than into the -1 because the kernel isn't very smooth. Okay, so I'm going to look at an example here. This is a multivariate normal probability. Sigma has been chosen in some particular way, arbitrarily, not any special way. Alan Gintz has a nice way of transforming this to reducing the dimension -1 to an integral with uniform measure. And here's our error bound. And so what we're expecting is that the error is going to go down like the discrepancy, because the norm of f will not change as n increases. This cosine may fluctuate between plus and -1, but it's not going to change a lot. It could get very small, but this is the term that changes with n, because as the sampling measure gets denser and denser, we're doing a better approximation of the uniform. And as I said, -1/2 for Monte Carlo, -1 for Sobol. There's what IID points look like. These are what unscrambled Sobol, because I'll look at scrambled in a moment. And this is what scrambled points look like. And here we can get order into the -1.5, or 3/2, plus a little bit. We can't do it with that kernel I just showed you, because that kernel I just showed you is too rough, but with a somewhat smoother kernel. And since it's randomly scrambled, what I'm saying is we can do it on average. So here is the error, the real error, because what I did was took many points till I thought I had a pretty good answer, and then I came back for a smaller number of points and plotted it. So I took 100 replications. The dot is the median. The upper part of the stem is the worst 90%, or the worst 10%, the bottom of the worst 10%. And so this is IID into the -1/2. This is unscrambled Sobol, which is into the -1 approximately. And this is Sobol, which is into the -3/2. And when Art looked at it like this, he said, it looks like it's going to into the -2. Why? And I said, I don't know. And I still don't know. When I do know, I'll let you know. OK, so a couple of lessons. Low discrepancy sampling is better. So what is this down here? I'm getting 10 to the -10 versus 10 to the -3. So that's a pretty good improvement, right? Oh, even without the scrambling, I get 10 to the -6 versus 10 to the -3. And if I randomize, I can do even better, because as was showed you, I think Art mentioned it, that the scrambled Sobol, which is a case of a digital net, is like stratified sampling in one dimension, but it's doing it in higher dimensions. So this should be reassuring. We know theoretically we have this for the discrepancy. That's the part that's changing. That's what the errors look like. Fine. We should be happy. At least it's good to be happy before we get worried. And right now, we're happy. Okay, so let me tell you a little bit about, because we talked about scrambling. You heard about shifting or about digital scrambling of nets. So the problem with this discrepancy is it's hard to compute. It takes at least order n squared. So let's suppose we have this scrambling transform, psi, that takes the unit cube into the unit cube. And let's call the filtered kernel, we take the expected value of the kernel with the scrambled of x and the scramble of t, where x and t are any 2 points in the unit cube. And let's suppose that, and when I say let's suppose that, I mean in the cases we're interested in, it really works out to be this way, that 1 is an eigenvector of this matrix, which is the filtered kernel, where you put in all the pairs of points that you have in your design, your net or your lattice rule. Let's assume that k0 is 1. That's just a normalization. Then the root mean squared discrepancy in terms of the original kernel is just the discrepancy, doesn't matter which scrambled version of your set you put in, of the filtered kernel. And this is only order n operations. So it's a very nice kernel. We sometimes call them scramble invariant kernels or shift invariant kernels, depending on what set we're looking at. So why do I think that's important? Well, it was interesting several papers or years ago, but I think it's important for another reason. because, for example, Art said you cannot compute the variation or the norm of f, which we call the variation. And he is right. Normally, it takes a lot of work to do. But in this case, for this kind of kernel, you can compute the variation of the minimum norm interpolant to your function in only order n, or n log n, which is about the same work as you're doing to get the integral in the first place. So that's why I think these kernels may be nice. So it only requires order n operations, or I'm sorry, maybe n log n. And these filtered kernels take the form, these are some eigenvalues. These are the eigenvectors. They're Walsh functions for digital nets, like Sobel sequences. They are complex exponentials for lattice node sets. OK. Next, I want to talk about the dimension effects. So here is our discrepancy, the one I showed you. Here is our norm. You get to see it again and scratch your head if it's new to you. And I'm going to choose d equals 1, because that's the simplest. 4, because there are 4 quarters in a year. 12, because there are 12 months in a year. 52, because there are 52 weeks in a year. And 250, because there are 250 trading days in the year. Just random numbers. OK, so when we put in the discrepancy, here for 1, it goes down like into the -1. For d equals 250, d equals 12 even, it's going like into the -1/2. Now, what happened? Did our theory go wrong? Or what went wrong? Well, it's going like into the -1/2. And what I've done a couple of things. First of all, I've scrambled them and taken the mean square discrepancy. Second of all, I scaled it, because there is a dimension effect just for n equals 1. So I've scaled them all so that at n equals 1, the mean squared discrepancy is 1. So I've kind of aligned them all here. But the point is that for high d, this discrepancy is going like into the -1/2. And it will get to into the -1 plus epsilon. But we don't know, or I don't know when. It will get eventually, because the theory says so. But not up to 10 to the 4, and maybe not in your lifetime or mine, depending on how high d is. So this is worrisome, because, well, it's not worse than Monte Carlo, but we would like it to be better. We like this. We don't like this. That's a factor of what, 10 to the minus, I don't know, 1.5 to 10 to the minus 3.5. It's a difference of a factor of 100, I think. OK, so let's do a d equals 12 dimension example. This is an Asian option. It's a nice example, but other examples can work similarly nicely. I try this example, and I get into the -1/2 for IID. I get the error, the real error, is into the -1, or just about, for both Sobel and scrambled Sobel. So the practice is better than what I would expect from the discrepancy plot, because the discrepancy is going like into the -1/2. And these are going like into the -1. In the previous example, this was into the -3/2. Why not? Well, actually, this function, the payoff function, has a kink. It's not smooth enough to be in the space of for the smoother kernel to get the into the -3/2. It's not really in the space to get the into the -1. But Ian and friends have a delicate argument to make it work. And you can take a look at their papers. OK, so I'm going to talk about these weights. Remember, I told you, get the fractor U correct. D or S is your choice, but not n for dimension. OK, here's the gammas. You have to get this right, or your paper may be rejected, even if it's good. So I'm going to take my kernel. This was my kernel before. This used to be 2 minus max. I'm going to stick a gamma in front of here. This gamma k is a coordinate weight. And I'm going to put it here, and then here, and then here. So if gamma k is 1, we get back just to what we had before. And so I put a gamma k here. I have to put a product of gamma k's for k and u down here. So these are what was called in an earlier talk as product weights. I'm looking just at one example of weighting. And if I look at this discrepancy, and if I choose my gamma k's k to the -3, because that's about as fast as you need, then I get all of the discrepancies line up at into the -1. Wonderful. So I got into the minus 1 where for d equals 250 before it used to be into the minus 1/2. So what does that mean? That doesn't just mean, wow, it's going to work. It means you have to look closely and see what we've done to mess up things perhaps somewhere else. So there is this gamma u. And if these gamma k's are small, the gamma u is going to be small, maybe very small. So in order for this term, the norm of f, to not blow up, we need these derivatives with respect to xu, where u contains large indices. That has to be small. So this is a way of explaining why, for that Asian option pricing example, we could get into the minus 1 when the original discrepancy didn't, because what we have is something like a situation where in this new space where we've weighted the coordinates, this is finite or not too large, and this is decaying like into the minus 1. So when you hear people talk about weighted spaces, this is one thing they have in mind, and there's lots of variations. And I really like the book by Eric and Henrik, who have covered all sorts of cases. If you want to look at the early history, see the paper by Ian and Henrik. And also Russ Kaflish and Art Owen and Markov paper. Yeah. OK, I'm going to catch my breath right now because let's see what I've tried to say. This error, the real integral minus my approximation, can be written as the product of three things. If you don't like the cosine, you can ignore it, then it's an inequality. This is called the trio identity. This is what Charlie Mung called it. And I like the name. And I've written a paper recently from my talk a year ago at QMC 2016, where I talk a little more about the trio identity. Without the cosine term, it's an extension of the Cox-Mihalkovskian inequality. There are other versions of this, a randomized version, a Bayesian version, which I'll talk about in just a moment. This reproducing kernel Hilbert space is used a lot, and maybe some of you know it, but I just picked one example integration, which is a bounded linear functional. Suppose you want to approximate a function. A lot of people want to approximate the function. You can do the same idea. So this reproducing kernel Hilbert space has a lot of applications, and my former colleague Greg Fosshauer and his former student Mike McCourt wrote a book which I think is a nice way of explaining some of what goes on. If you don't like Hilbert spaces, you want to be more general, you can do things like this in Banach spaces. Pierre talked about attacking the error analysis by Fourier analysis, Fourier sines and cosines, or Fourier-Walsh for the Sobel sequences. I won't be able to say much about that. If you choose a kernel that has the special formed, what I call the filtered type kernel, then this discrepancy and a lower bound on f can be computed rather quickly. Otherwise, they're expensive. So I would say I think we should be paying more attention maybe to some of these special filtered kernels. And one question I don't know the answer to, but maybe someone in the audience does, we heard about higher order nets. So they're really good at getting faster than into the minus 1 convergence. What is the appropriate filtered kernel that you can put any higher order net into, and then you will automatically get the decay of into the minus 2, 3, plus epsilon, and so forth? I don't know what it is, because back in the day when I was working with him, we were only hoping for something like into the minus 1, maybe into the minus 3/2. But I think it would be subtle. And yes, Dirk, I'm looking at you, because maybe you know the answer, or someone does. If you do, I'd like to talk to you about it. Okay. Some people are interested in adaptation. Okay. If you can estimate this norm and you can compute the discrepancy, then you can talk about adaptation in terms of the sample size n, and I've done something like that in a different context. But if you're talking about where to place the next point, the only thing that this tells you is something totally independent of f. So if f is really active over here, that error bound doesn't say put the point over here. It only says your sampling distribution is not uniform enough, put the point over there because you're missing points over there. And so whereas in one dimension we have these adaptive routines that put points where the action is and ignore where the action is not, I don't think the error bounds yet tell us that. Some maybe, but okay, we don't have enough. Let's say we're supposed to be thinking about problems we can solve in the next year, and I think that would be an interesting one. And part of the problem is in high dimensions, it's hard to locate a thin peak in high dimensions. Okay? So maybe it's not dimensions, maybe it's directions that we should be sampling more carefully in. But that would be also it. Okay, the discrepancy. The decay rate can be improved by choosing the quasi-Monte Carlo sets. Clever randomization improves things. It depends on the reproducing kernel. So you change your reproducing kernel, and you may get some different behavior. Yes, here's my question. What is the right appropriate kernel for higher order nets? Oftentimes, as was mentioned, if you are not interested in uniform points on the cube, you will do a transformation to get them to be, say, Gaussian or whatever else you want. That's just what's done in practice. And there are other ways of measuring uniformity: covering radius, minimum distance between two design points, the power function, and so forth. But this one works for integration. It may not be the best for other types of problems. Okay, so I'd like to mention a couple of working groups. There is one on representative points, and another one on sampling and analysis in high dimensions. Both are concerned with how do you place the points. So we'll be looking at maybe how do you make this discrepancy not asymptotically small as n goes to infinity, but n is, in some cases, for the small data, samples are expensive, n is small. And so how do we do a better job of that? There is working group. I've called it Art Owen because I think it's a working group, but I'm not sure yet. You need to confirm, which was tuning QMC to the specific integrand of interest. For example, knowing about these weights, which Art talked about. And so I hope that becomes a working group. But I don't see it up on the website yet. Variation. I think it's important to note that although it doesn't affect the convergence rate, if you choose your way of making mu equal to this integral well, maybe by a variable transformation, maybe by importance sampling, then you can substantially reduce the errors. And that is probably more of an art than a science. Let me skip that. Okay. Let me give a few thoughts on Bayesian cubature. So this is the idea: f is not a deterministic function, it's a Gaussian process. Maybe the mean is 0, but here we have a covariance. And then the error becomes a normal 0, 1 random variable, standard normal, times this quantity, which we can compute, where the matrix C and the vectors little c are defined above, and an S. Now this S is part of the assumption. So you can't just assume whatever you want to. You need to estimate it by maximum likelihood. And probably the C has a parameter embedded in it, which also may need to be estimated by maximum likelihood. Well, if f really is a Gaussian process and a typical one, then the error is going to be, with 99% probability, less than or equal to 2.58 times the standard deviation of the error. So now we have one way of saying that if this gets small enough, we can stop. Because we can estimate this by maximum likelihood. We can compute this because it's just formula that depends on our design. And 2.58, we know. Problem. For typical C, it takes order in cube operations to invert this matrix. If we don't want to do order in cube, it's too expensive in general, unless you choose some special kernel. So, but there are some people that have been looking at faster ways to compute this. And there is a working group on probabilistic numerics, and I think we'll hear a couple talks later, that along this line of if f is a Gaussian process, maybe you can say more. So I would like to, this is a Matern kernel. Here is the decay. I cannot go in very large because I run out of patience because I have to do order n cube operations. And it's supposed to maybe be into the -2, but I'm not convinced, so I just can't tell you. This was our Gaussian problem. Okay. And first time I did it, I got 98% correct, but then I found a bug in my code, and now it's only 83% correct, which is not 99% correct. So I would say it's promising, but maybe has some more work to do. Okay. Because I have little time, I'm going to quickly talk about some work we've done of how to choose the n. I can't really speak about this slide, but I can show you some examples. So, Asian option problem. Ran 100 cases. We used the principal component analysis for generating our normal random variables. Scrambled Sobling with control variates. It took at worst 4,000, and the time was about 200ths of a second, and we got it correct all the time. Bayes rule, not the Matern kernel, but what I just showed you, but with a lattice kernel, so I can do things fast. It's one of those filtered kernels that I say we can do things fast. Also got it almost all the time, a little more expensive. Gaussian probability. I'll show you the last part, and you can look at the slides later. Pretty fast. The error is really much smaller than we need. But this is with a smoother kernel, because this is a very smooth function, the Gaussian probability. There's no kinks. And finally, the logistic regression example. And this one we're still working on. And I want to be honest. Well, first of all, I was just working. I got the code from Khan just recently, and I ran it. So maybe my problem. But this looks nice because I don't know the answer, but everything is within a box of 2 epsilon. So that's good. But sometimes it's not. And so I can't be confident that this is working, but it's an example. And you can look in the paper with Tony and 2 of my students. How do we decide that this quotient of integrals has reached the correct answer? And there's some subtlety, but that's spelled out in the paper. And so I think this is something that we need to do more looking into. It's not guaranteed, but it's possible. OK, so the main thing I'd like you to see is reproducing kernel Hilbert spaces. This is an important tool. And if you're new to the area, I'd really encourage you to learn about them from the talks here, from other sources. And I think you may find it useful even if you're not interested in integration problem. The quasi-Monte Carlo point sets, we can get improvements of 100, 1,000, because we are getting asymptotically faster rates of decay. Whether the bounds fit what we observe, well, depends on if the integrand is typical. So sometimes yes, and sometimes no. And sometimes the integrand doesn't fit the theory, but it still works out well. And practical stopping criteria, which are of interest to me, is still an area which we need to do a lot more work. Thank you. I think it's better to scramble Sobel because Sobel, the way it is always sort of biased towards the left or downwards. It's like a left rectangle rule. So I would say the amount of effort to scramble is very little. And I would encourage, I mean, Art even mentioned that sometimes you're going to map onto the real line and you don't want minus infinity because it's not so good. But I just think typically, even if the rate isn't any better because the problem isn't smooth enough, you still often get a improvement in the constant. So yes, I would say 2.
The reason I asked you was if you just don't scramble, for lots of examples, the rate of convergence is almost similar. However,
almost similar to what?
You don't see much of a change compared to a lot of examples in which you have n to the -3 half. Sometimes you have, sometimes it's into the -1.
Without scrambling, you're not going to get into the -3 halves.
That's right, yeah. I think so.
With scrambling, you may.
It seems like sometimes you get better, sometimes you may not get better. Is that right?
Well, so if I may go back to here. Okay, here was a faster rate of decay. The problem was smooth enough. Here was not a faster rate of decay, but a better constant.
Okay.
So, because it wasn't smooth enough. So, yes, you may not improve on the rate of decay, but I think you'll typically improve on the constant.
Thank you.
I can cook up a problem which you won't, but
Okay. Thank you.
okay, so yes. Sorry. So the question is, could you choose a kernel so that that matrix, which could be huge, is sparse, and therefore the inverting would be cheaper? So I don't know this well. I can imagine yes, because there are some kernels that have compact support. And so they say the only points of importance, if I want to know what happened here, are the points very close by. But I'm a little worried about doing that in dimensions 10, 12, 100, and so forth, because I'm afraid we may end up with hardly any points. So perhaps, but I don't have a good feeling of how well it might work out.
Because this is a question people in UQ are looking at, choosing some ANOVA kernel and finding the dimensions which are not important. And I think this related as a question of
so if you're ignoring dimensions, I'm not sure if that would make your matrix sparse, but maybe you have to tell me more about it. Yeah, that's a good question. No and yes. No, I'll tell you a little more about that. Okay. The smoother the kernel, the more and the denser the sampling, the more likely to be ill-conditioned, which is definitely a problem that people find, especially in small dimensions, and especially for, let's say, the squared exponential, also known as the Gaussian kernel. These kernels here we're often using are not that smooth because the examples sometimes are not that smooth. So if you have a really smooth example, like the question earlier, and you want to choose a really smooth kernel and the dimension is small, yes, you're going to have ill conditioning. And I have run into that. So that's an important aspect. And because this matrix is sort of like the square of two matrices, you've somehow made your problem worse, even though the kernel is a very nice construct. And so one of my students who's working with me, we've been looking at that. But as the dimension gets bigger, then I think you have that problem less. So it depends on the particular application and how large n is and how large the dimension. Yes, unscrambled. I mean unscrambled with a 0, yeah, starting at 0. No shift, no scramble. I didn't try that. Because as you said, yeah. Maybe. Because you said I liked MATLAB, and I don't know how to do shifting without scrambling in MATLAB, so that's my my weakness. I'm computationally weak. Yeah. The symbol is the median. Here is the bottom of the worst 10%. Could be. Yeah. Yeah. Could be. It's an interesting question. It's just not risen to the top of the questions I had time to look at yet. But yes, you could be. Yeah. Yeah. That's something I hadn't thought of. So thank you. That's a good suggestion. Do you know how to tackle that to find the median square discrepancy?
Hi, could you go over the fast kernel that you had? So the kernel where you could compute the bound.
Like here. Mm-hmm.
So could you give us some more details on how
okay.
it's built? Or?
For lattice node sets, basically the kernel is a function of x minus t mod 1. But it has to be a kernel that is still positive definite. And that's what you want to do with the lattice node set. If you're using Sobol or digital nets, you got Walsh functions, and I don't have an easy way to explain it. But if these lambdas are positive, then this decomposition, which L is going over some infinite range, guarantees that it'll be of the right form. The thing is, you have to find something that you can sum, because you want to be able to evaluate this kernel without doing an infinite sum. But you saw the Bernoulli polynomials in Pierre's talk. Actually, that's an example of the filtered kernel for lattices. If you remember what he called P alpha, that, with some change of notation, would be essentially that kernel. And people, when they're looking for computation, looking for good sets, they will often use something based on this kind of kernel because it's faster to evaluate.
She's been in the picture, you know, on the QMC world for many years, working on digital net, lattice rules, and so on. And right now she's focusing a lot, at least she's working a lot on differential equations and using quasi-Monte Carlo methods in differential equation. And that would be the topic of the tutorial.
Thank you very much, Pierre. And thank you, Ilse, for having me here and together with my co-organizers for this QMC program. And thank you all for being here. So I've been asked to give a tutorial on the application of QMC to PDE problems. And I'm a little bit greedy. I want to add a bit more things than just PDE, because I think there are already many people working in QMC for PDE applications, and there are still many open problems. So this is still a good topic if you want to get into this application. But I think we learn many things from working on these PDE problems, and some of the experience, I'm sure, actually would apply in other applications. And some of you here coming from outside of QMC, you may have an interesting application, new application for QMC. And so maybe you will see some of the things we do here, and then you might say, well, there's similar characteristics in my problem. And this is hopefully some starting point for some new working groups here. So the audience here is very mixed, I think. You have some real experts in QMC here. And there are also people who may not have heard about QMC so much. My talk is to those of you who don't know QMC, okay? So the ones who know a lot about QMC, I'm going to ignore them. That's my plan, okay? So you can go to sleep now, Greg. Okay, right. But then I will also mention some of the more recent work on QMC, mainly to just mention some headings to give you some idea what they are. And I'll mention some of the experts here, and then you'll be able to listen to their talk later on in the week to get to know more of the details. Okay, so I list a big list of collaborators. These are the collaborators that I worked on in the area of QMC for PDEs with random coefficients. Later in my talk, I will also talk about some cost reduction, cost saving strategies, and that includes some other collaborators listed here. So just quickly, so the people here, okay, Dirk Newens is here. Christoph Schwab will be here later in the week. Ganesh is here. Mike Giles is here. Greg is here. Alec will be here later tomorrow, and Ian is here. So there are actually many people here who you can talk to. If you don't want to talk to me, there are other people you can talk to about this topic. Right, so the outline of my tutorial today is I'm going to start with a motivating example for the PDE application. Some of you may have seen it before. And then I want to just very briefly go over some background quasi-Monte Carlo results. So you've already had 3 excellent tutorials on QMC methods, looking at QMC from sort of different angles. And I want to talk about it from the perspective of the theory that we need to apply to these PDE problems. So it'll be a bit of a slightly different angle to things. And I try to keep things not technical, just I want you to get the picture. And then I'm going to talk about how we can apply the QMC theory to these PDE applications, assuming that you don't know much about PDE, like myself when I started in this area. So it will be very basic idea of what are these PDE problems, what are the characteristics of these problems that we need to make use of. And hopefully, you will be able to transport that into your applications and see how we might then learn from this experience. I mentioned some cost-saving strategies I want to talk about, and if I have time, I'll talk a little bit about software. That's roughly the outline. Okay, so this PDE motivating example, we have a system of a coupled PDE describing groundwater flow, for example. So you can imagine this as a thin slice of rock on the ground, a thin slice of rock where you might have flow going from left to right, blocked off above and below. So this pointer is not working. So you have flow going from left to right. And you can imagine that you may have this channel, this white part, is describing the part of the ground that's more permeable. So you can imagine you have flow of water coming from the left to right, and there's like a channel following this white part. Okay, so imagine if you place a piece of particle on the left-hand side, after 1 unit of time, you might see that this particle follow this channel and might end up here. Or you might have a different realization of this rock on the ground. So it might be this picture on the right-hand side. And then if you, again, place a particle on the left, this time, this particle after 1 unit of time may be stuck here because this part is less permeable. Okay? And because you don't know the structure of the rock on the ground, This is typically modeled as a random field with some given covariance structure. And every picture like this describes a realization of this random field. And what do they do? Okay, so because this coefficient A, this permeability coefficient, is unknown, we model it as a random field, and therefore there's a random element to this PDE solution. So the uncertainty in the solution, like the pressure of the field or in the velocity field, and so any quantity of interest that you want to compute is an expected value with respect to this randomness. Okay, and so typically what people do with the Monte Carlo simulation is that people would generate a number of realizations. So you have a number of these cloud images, okay? And for each cloud image, you go and solve a deterministic PDE, corresponds to each one of these generated coefficient 8. So for each realization, you solve the PDE using your favorite method. And then if you've taken 1,000 realizations, you would have 1,000 different solutions. You take the average of the solution, and that would be the solution to your final problem, okay? And you can look at the spread of these, for example, 1,000 solutions to get an idea of some statistics. So for example, in particle dispersion, you might have, like I described before, you might have 1,000 different realizations of this rock on the ground. You release a particle here, and after 1 unit of time, you want to know where the particle ends up. I do this 1,000 times. I have these 1,000 different possible positions of where this particle might be, depending on what the rock looks like on the ground. And you look at the spread of these 1,000 numbers, it gives you an idea of the distribution of these points. And also, you can look at the mean. And for example, nuclear waste buried underground, you want to know after, say, 100 years, whether your nuclear waste is still going to be confined within the region. So this is like travel time, and see how easy it is for the particles to get out of the region, and so on. So this is the application, motivating example. Right, so what do we do with quasi-Monte Carlo? Because the expected value, by definition, is a high-dimensional integral, with the dimensionality as high as the number of parameters that you need to describe this randomness, okay? And so this is where quasi-Monte Carlo method comes in. It comes in when we are approximating these very high-dimensional integrals. In these PDE problems, the dimensionality, the physical dimension, might be 1 or 2 or 3. We live in the real world, probably 3 dimensions at most. That's my D. D is the physical dimension, D is small. 1, 2, or 3. But in my talk, S is the number of stochastic dimension. That's the number of random parameters you need to describe the problem. And this is where the high dimensionality comes in. This is where quasi-Monte Carlo works. And you have already heard in the tutorials before, with quasi-Monte Carlo methods, we want to achieve better than the Monte Carlo convergence rate. 1 on n perhaps, 1 on n squared perhaps, depending on the smoothness of the problem. Okay. So there's your motivating example of these PDE problems. So what do we actually want to do? We want to use quasi-Monte Carlo method. This is just a few slides, just a recap of what you already heard so far. In the unit cube, let me start the talk in the unit cube. The classical theoretical analysis for quasi-Monte Carlo methods have always been formulated over a unit cube, okay? But realistic problems typically are not. And there's something about this mapping from the cube to the Euclidean space. This is considered as change of variables, change of measure, or mapping. This is very important to make sure that the integrand is nice and easy for work. So for the moment, let's just restrict to the unit cube. Monte Carlo methods and quasi-Monte Carlo methods take the same form in the unit cube. With quasi-Monte Carlo methods, we try to choose the points deterministically to make them more uniformly distributed in the random point so that we can get better convergence rate. And in practice, we want to use randomized QMC methods to remove the bias and also to allow for error estimation. So we already heard a few talks about that. There are 2 families of quasi-Monte Carlo methods, the digital net and lattice rules. And in my opinion, the most important development of QMC in the last, say, 10 or 15 years are these 2 aspects. The first aspect is this construction in high dimensions, the component by component construction. These days, we want to work with problems with dimensionality really, really high. And I'm talking about hundreds of dimensions, thousands of dimensions. Or in fact, in these PDE examples, we're looking at an infinite dimensional problem. Okay, so you really want very, very high dimensional integrals. And so the classical quasi-Monte Carlo theory didn't used to give you a way to construct points to really, really high dimensions. And so this component by component algorithm, as Pierre already mentioned, allows you to construct the parameters for these quasi-Monte Carlo methods one component at a time, or one dimension at a time, so that you can keep extending it to 1 million variables if we need to at a low cost. So that's one of the important things. The other important development is the higher order digital net. This is when your function, your integrand may be very, very smooth, and so we can exploit the smoothness to get higher order convergence rate than 1 on n. So 1 on n squared or 1 on n cubed, okay? And in this PDE example, I will say that I will tell you why it works in a minute. Okay. Lattice rules. So the component by component construction for lattice rule, component by component construction is easier described for lattice rule. A lattice rule, as Pierre already explained, it's easily, a rank 1 lattice rule is specified by an integer vector. And so you can just enumerate the points with the vector. I won't go into the details here anymore. The quality of a lattice rule is determined by the choice of this generating vector. And we can also add a shift to get a shifted lattice rule. You've seen this already before, so let me just move on. I'm just showing this slide very quickly and move on. So this is quite a number of research papers in this area on the construction, on the theory, on the function space settings, which I actually don't want to go into today. I only just want to mention that we have a way of constructing lattice rules that allows you to go one component at a time, to constructing this integer vector one at a time to get you to high dimensions. We can do this using FFT, so that the construction cost itself in some settings is only linear in the dimension and is only n log n in the number of points. Okay? The convergence rate can be optimal depending on what function space you're working in. If you're allowing your functions to have mixed first derivatives, then you can get first order convergence. And in more general settings, you can also get higher order convergence for periodic functions or for non-periodic functions using these higher order digital nets. Okay, so this is just some basic background theory, and the extensible version is already mentioned in the tutorials before. I mentioned some website. Dirk Nguyen's website has the construction code and also for the generation codes for QMC points. Okay, so back to QMC for PDEs. Now, again, I'm talking to you as you are not an expert of QMC and also probably not an expert of PDEs. Okay, so I list here many, many people and many, many papers. The point is just say that there are already a number of work and progress in this area. And why is this PDE problem become so popular all of a sudden from the QMC point of view? QMC has been known to work in many different applications very well. In fact, probably many of you heard of QMC work well in finance problems. And when I started in Sydney in 2003, we also looked at applying QMCs to some statistics problems, and they also work well. The reason that QMC becomes popular in the PDE world is because, maybe I should go back one step. QMC works in these finance problems that we know, but we were not able to really explain why QMC works. And this is because QMC require the theory of QMC method typically require you to have some knowledge of your function. Your function needs to be smooth, and so on, and so on, and so on. And for these finance problems, the theory does not work. Okay, and so you can apply QMC to finance problems, and then it works well, and that's as far as it goes. We can't say much more. But with these PDE problems, we can, because the PDE problems can be shown to satisfy all the theoretical requirements that you need for QMC. Okay, and there must be other applications out there that will have the same structure. As a few tutorials before already talked about, QMC methods, I can't quite remember. I think it was in Fred's talk with these plots of the discrepancy function. With the discrepancy function, it goes up to infinity so fast with dimension going up. people find it hard to believe why QMC would actually work in these high dimensions, right? So the fact is QMC works with these high dimensional problems not because QMC works all the time. It's because QMC can exploit the hidden low-dimensional structure of the integrand and this effective dimension result. So what we have here is a PDE problem which has those structure. Okay, so let me get into what we mean by that. So I mentioned here quite a number of papers. It started in 2011. We had a computational project in paper 0 where we simply just try QMC method to these PDE problems. No theory, and the results was very good. So we try to extend this. We try to explain theoretically why this worked well. And there's been many, many papers in this topic. I will mention here that I color-coded things because to be able to get the different convergence rate, to be able to apply the QMC theory to these different PDE formulations, you actually have to tap into different QMC theory, okay? And I don't want to tell you exactly what each theory is because it's just messy. I just want to give you an idea that they're actually different things you got to look into. So the 3 different settings means you're working with different function spaces, sometimes paired with a different kind of quasi-Monte Carlo methods. And this is actually an important part. You may have heard some theory on QMC. You might have also at the same time separately heard some different QMC methods. And you say, OK, I can use Sobel points, I can use Houghton sequence. But you can't just pick things and mix them as you like. You have to pair the right kind of QMC methods with the right kind of function space setting to be able to get the theoretical convergence rate you need. And also, depending on what sort of formulation of the PDE problem, which I'll explain in a minute, the uniform problem and the log normal problem, you need to tap into different theory. Also, if you want to have a single-level algorithm or multi-level algorithm, the theory is a little bit different. And this is why there are so many papers out there on PDE, QMC applied to PDE problems. And let me now give you a little overview. OK, so I'm taking one step back to this general theoretical understanding of how we apply this QMC problem, QMC methods to PDE problem. I put 5 minutes on this slide, but I think I'm going to talk for 10 minutes here. This is the experience so far. I think this is the most important slide, actually, for you people new to QMC. And the concept has already appeared in the 3 tutorials before, so I'm just re-emphasizing the same thing. The common feature among all 3 QMC theoretical settings and amongst most of the existing QMC settings are as follows. First of all, there's a separation in error bound. Okay, I have an inequality here saying that the QMC error is bounded by a product of 2 factors. The first factor, what I call the worst case error here, depends only on the QMC sample points. Okay? And the second factor here, which I've called the norm of integrand, depends only on your integrand. And this separation allows you to sort of focus on one part at a time, the integrand or the QMC or the quasi-Monte Carlo sample points. In fact, in Fred Kicknell's tutorial before, he actually had an equality. He has a trail identity, which includes also a cosine factor. I think he used to call it the alignment or ill alignment part. So it's a similar concept. In Art's talk, this is the Koxma-Lufka inequality. Okay? Basically, a separation of error is a product factor of 2 parts, that you can focus on the sample points and focus on the integrand. In the classical quasi-Monte Carlo theory, what would happen is you will be given an integral that you have to evaluate, and here's your integrand, okay? And I would say, okay, you've given me the f, so I put in f here. Maybe here I have the star discrepancy for the worst case error, and I have the variation in terms of Hardy and Crosser as the norm. And you have given me the function already. I check the variation, and that's it. How big or how small, that's fixed. Nothing else I can do, so I put that aside. I then try and work very hard on getting a set of quasi-Monte Carlo methods to have really small star discrepancy. That would be the classical way of thinking, okay? But the way we like to think about quasi-Monte Carlo methods today is a bit different. We want to actually be able to tune our choice of the sample points given the function, okay? So we want to have the freedom to work with, sorry, the pointer doesn't, oh, yes, doesn't work. Okay, we want to be able to find a way to choose the function space that we work with that's better suited to the given problem at hand. Okay, and that's why they are different function spaces. Because maybe you have a function that I'm best using this function space. You might have a different function, and I will use a different function space. Yes, okay, that might work better. Yes, it's better. Thank you, Brett. Okay, so I want to be able to play with this function space. That means I want to be able to work with different norms depending on the function you give me. Okay, and I also want to use different kind of quasi-Monte Carlo methods to make the corresponding worst case error small. So that's the mentality these days. Okay, so that's the first point. The second point is QMC methods will not work well for every kind of problem. Actually, QMC methods work well when a problem has low effective dimension. So we want to exploit this, that the function may be only important in the first 100 variables, or maybe only the lower order interactions are important. So we want to be able to capture this in the theory by using weighted spaces. And Fred already explained this, and Pierre also explained this. This weighted space setting basically introduces a set of parameters which are called weights, gamma, and they will basically tell you which variables are the important ones and which variables are the non-important ones. And what we want to then do is we want to then pair the right kind of QMC method with the right function space to get the optimal convergence rate. And in fact, we want the convergence rate to be independent of the dimension as well as the implied constant. Everything we like it to be independent of dimension. And that's going to depend on whether your function has the right structure that we need, okay? And we want to then construct this tailor-made quasi-Monte Carlo methods, use these fast construction that can allow us to go up to tens of thousands of dimensions and millions of points efficiently. Okay. And we're also more greedy. We want to use these embedded ideas so that you can, in practice, add more sample points to your calculation when the error is not small enough. So we want everything. We want independence of dimension. We want a fast way to construct the points. We want everything to be independent of dimension, and we want the rule to be extensible for use in practice. That's the idea. Okay. And so that all sounds very good. So what do we do when you come up with a practical problem? How do I actually apply the theory? Well, the first step in applying the theory is that you need to make sure that your function actually lies in my function space. Otherwise, all bets are off. We can have beautiful theory, but it doesn't apply. Then that's pointless, right? So to make sure that your function lies in my function space, I have to actually choose the function space as well. Okay, because in the QMC theory, there are many different settings. Okay, so depending on the function you give me, we might be able to find the best function space to analyze your integrand. Okay, so once I have that, and I want to have an idea of how big the norm is, I need to estimate the norm. So once we can estimate the norm and have an idea of how big it is, I hope then to find a way to choose the weights which describe this particular shape of the integrand, the dimension structure of the integrand. And this weight, these parameters, affect not just the norm, but also the worst case error. And in fact, this is normally a trait. Sort of the weight here sits on the denominator of the quantities here, and it sits on the numerator here. So if you make this really small, this will go big, and vice versa. So there is actually an optimal choice of weights which will minimize the product factor. So it's not important to make one of them small. You want actually the product to be small. And so the mentality is, once I know how to estimate the norm, I can then try and choose the weights to minimize this product, and I will then choose the sample points by minimizing the worst case error after the weights are chosen. Okay, so I think I spent 10 minutes on this now. So then, this is how we apply QMC to PDE problems. The rest is just technical details. Okay, right, so let's have a look. So this is a very brief overview of the PDE analysis. So I want to talk about PDE with random coefficients in the two very popular settings, the uniform setting and the log normal setting. You probably don't know what they are. I will explain briefly what they are in a minute. Okay, so we have two different settings in the application of QMC to PDE problems, and I'm going to make use of three QMC theoretical settings. I'm not even going to tell you what they are. I'm not going to show you what the norm looks like, not at all. I'm assuming you are new to QMC for the first time. You've only heard 3 tutorials up to today. Okay, so I have 3 settings. What are the differences? The first one is more of a classical standard setting, if you like. We have integrand formulated over the domain of the unit cube, and I'm going to use randomly shifted lattice rules. Okay, and with this pairing, from the theory of QMC methods for lattice rules, we know that we can prove that if your integrand has mixed first-order derivatives, you want to be able to differentiate once with respect to each variable. If you have integrand with this property, then we can get first-order convergence, 1-on-n convergence for lattice. This is the QMC setting 1. QMC setting 2 is a setting where we move into the domain, which is the Euclidean space. Okay, so this is a setting where some change of variables is required because QMC methods are typically living in the unit cube. If you have something living over the Euclidean space, you have to do a mapping. And a standard mapping is, for example, by using the inverse of the cumulative normal distribution function. But that's not the only way. Okay, there are other ways you can do the mapping. And so there is a setting which says if I use some mapping, and that mapping you use is taken into account to derive the theory, the construction of the randomly shifted lattice rule, then if your integrand also has mixed first-order derivatives, in this setting, we can also guarantee a 1-on-n convergence rate. Okay, and depending on, like I said, depending on how you choose the mapping between the Euclidean space and the cube, you will construct lattice rules differently. So that's one of the settings. The third setting is we are back in the cube, but this time we want to get higher order convergence, right? So if you know that your integrand has mixed higher order derivatives, you can differentiate more than once in each direction, then we can make use of something called interlaced polynomial lattice rule to get higher order convergence in this setting. Okay, maybe without any technical detail, let me just quickly explain to you what interlaced polynomial lattice rule are. So Pierre already mentioned lattice rules, and I think he was going to talk about polynomial lattice rule, but run out of time. So in Pierre's talk, he explained how lattice rule work really nicely. For a rank 1 lattice rule, you need one integer vector to describe the lattice rule, right? So if you have a 100-dimensional rule, you need 100 integers, okay? In a polynomial lattice rule, instead of 100 integers, you need 100 polynomials. That's it. The rest is basically just technical details, okay? So instead of 100 integers, you use 100 polynomials, and that gives you a polynomial lattice rule. A polynomial lattice rule looks like a polynomial, but it is actually a digital net in disguise, okay? So a polynomial lattice rule is more like a digital net. It's actually a digital net. It just looks like polynomial, but it's not. It's a digital net. Okay, so at this point, they are the same. Okay, you analyze them in different function spaces, but you get order 1-on-n convergence and so on. To get higher order QMC methods, you use something called interlacing. So you take a polynomial lattice rule, say instead of 100 dimensions, you take 200 dimensions, and then you interlace them. You write them in digit expansion of the points, and you just basically do this. So if your original expansion of a point requires 50 digits, after you do this, you basically need 100 decimal digits, binary digits to do this. With higher precision, you can get higher order. Okay, this is the general idea behind how it works, and this is the work of my colleague Joseph Dick from Sydney. Okay, so that's the 3 QMC settings that we're going to use to manage this application to PDE problems. And I want to say that there's also a setting 4. What would you think would be a good setting 4? QMC experts are not allowed to answer. So for those of you who come to QMC for the first time today, you've heard 3 tutorials, this is number 4. And what I have said here, what would you think would be a good setting 4? General finite, well, okay, any domain which is bounded, you can do a linear mapping, and that will give you the cube, actually. So this is unbounded, this is bounded. Well, okay. Obviously, the mapping is very crucial, and it's a difficult, very difficult question here. Yeah, okay. Someone there was going to answer? RDS, thank you. So R to the S with higher order convergence, right? So this would be the next thing. I would like to have a QMC setting for which gives you the Euclidean space and higher order. Okay, and I tell you, at the moment, this is an open problem. Okay, well, it's not completely an open problem, actually. There are already quite a few groups of people working on this, but there's a catch. So far, all the analysis that I know of from the QMC world gives you setting 4, but has a dependence on the dimension S, which is exponential. The result that I mentioned here in these 3 settings basically says if you work in a nicely weighted function space with these weight parameters behave nicely, there's no dimension dependence at all. No dimension dependence. This is what we're talking about in the 3 settings. I can make error bounds independent of dimension. We can make the constant independent of dimension. Convergence rate independent of dimension. But setting 4 at the moment is still an open problem in QMC. How to make a higher order quasi-Monte Carlo method convergence in the Euclidean space with no dependence on dimension. Okay, so some of you may want to start thinking about that. Okay, so at the moment, these are the settings that I have to be able to work on the PDE problem. So what do we do? Okay, so the PDE problem, let's now look at a very simplified formulation of this flow problem that I started off with. So this is just a simplified elliptic PDE with homogeneous boundary conditions. And I have a forcing term, which I call kappa on the right-hand side. And everything is now written as a function of x and y. Okay, so x would be my spatial variable. So this is r to the d in the domain. Imagine this is just like a unit square or the unit cube in 2 or 3 dimensions. Okay, so this is a physical variable is x. Y is this vector of random variables, random parameters that we're going to use to describe the randomness. So A is the coefficient. This coefficient in this simple formulation of the uniform case basically says we write this coefficient A, xy, as a linear expansion in terms of these independent uniform random parameters between -half and half. So all these numbers yj are between -half and half. They are independent of each other and they are uniform. Okay, so this is the uniform case. And so if you are interested in some quantity of interest, which is a bounded linear functional, so I want a solution of my PDE, which would be a field, and I take the linear functional of this so that this is a number, then I can be interested in the expected value with respect to this random parameters y, and that is the integral that we might be interested in. Okay, so this is the integration problem over a bounded domain of -1/2 and half, raised to the power of n because I have infinitely capital this is boldface n, natural number. So we have an infinite sequence, infinite series expansion. Okay, so this is called a uniform problem, not just because we have uniform random numbers here, but it's also because we typically have to make assumptions that this coefficient A is actually uniformly bounded above and below. So A of xy is bounded by A max, bounded by A min, bounded away from 0. And this is to be sure that this PDE formulation has this unique solution and the standard uniformity, ellipticity conditions are satisfied. All these PDEs business that I don't know so much about. So that's why it's uniform. And so for QMC, this is a very obvious application of QMC methods because a unit cube, 0, 1, can be easily picked up and shipped by a half to -half/half. Okay, so we can apply QMC method pretty much directly to this formulation of the problem. Okay. The other formulation, which is called the log normal formulation of the problem, is that you have the same formulation of the PDE, but now the coefficient A is no longer a linear expansion, but it's e to the power of a linear expansion. And also the parameters y, rather than being just uniform numbers between some in a bounded domain like this, you have y will be real numbers, and they are normally distributed. So this is normal with mean 0 and standard deviation 1. So these are numbers now in the Euclidean space rather than in the cube. Okay. So that's the log normal problem. Okay, so PDE formulation is the same, just the coefficient A looks different. One is linear, one is e to the power of linear, so therefore it's not linear anymore in y. And the goal is again similar. Okay, so we are now wanting the expected value from bounded linear functional of the solution, but here the parameters are normally distributed, so you need to multiply by the density. And so in this case, we have a product density with the standard normal. So phi norm means the standard normal density for each parameter y. And we need to integrate over the Euclidean space. But we need to be sure to sort of restrict it so that these sums are all finite, summable. Everything here is summable. That's the formulation in the log normal case. And this is when the standard QMC method doesn't quite work because this is in the Euclidean space. And this is why we need the setting 2 where we want to be able to apply some mapping between the cube and the Euclidean space to be able to apply the QMC methods. Okay, so there's my really elementary introduction of the two kind of popular problems that people work in PDE with random coefficients. That's it. Okay, I don't want to go into any more than that. So let me just explain a little bit of what we actually do. Okay, so in the uniform case, which is the easier, more standard case, and if I use a single level algorithm, I'll explain why I use that term later, then our approximation looks like this. We have this integral that we want to approximate, a bounded domain, infinitely many variables, and I want to solve the PDE and then apply the linear functional. Okay, the approximation involves 3 stages. The first step is that we have to deal with this infinite series expansion. We can't do it computationally in practice. We have to truncate it. So truncate this to S terms. That's the first thing we do. Okay, so this is the superscript S means dimension truncate. Truncate the infinite series to S terms so that I can compute it in practice. Step 1. Step 2, I have a PDE here, which I do not know the exact solution. So we approximated it with finite element method. Okay, so this is my subscript H. So this H means I have to solve the PDE using finite element method. And then the third thing we have to do is we have to approximate this integral, now S-dimensional, okay? Because it's being truncated to S terms. I have an S-dimensional integral. I now apply quasi-Monte Carlo quadrature. And so this is where this integral is now replaced by an equal weight sum for the QMC points. Appropriately shifted, right? Because this is not the standard unit cube. Okay, so to analyze this error, this would be a balance of 3 sources of errors. The dimension truncation error, the finite element error, and the quasi-Monte Carlo error. Okay, so that's the 3 parts that we have to manage. And for the quasi-Monte Carlo part of the error, this is the part that we're interested in, we need to remember this error bound, this 5-minute primer. You have the QMC error bounded by the worst case error times the norm of the integrand, and I said that the first thing you have to do is you need to estimate the norm of the integrand, right? So the first step, the most important part to apply the theory, is we need to have some idea on this weighted norm of my integrand. So the integrand is G of the truncated solution of the finite element solution, okay? And to estimate the norm, we need to find out get some idea about the derivative of this integrand. And this is what I mean by differentiating the PDE. Okay, so once you have some idea about the norm, that means you have some estimate on the size of the norm. Then you have some bound on the norm here, and we also have some theory on quasi-Monte Carlo methods, which will give us an upper bound on the worst case error. We can choose the weights parameter to minimize the product, and in some cases we end up with something we call pot weights, which Pierre already advertised for me before, weights of the form which is include the product factor and also include the order-dependent factor. And we can feed that into the construction of the lattice rules. Okay. You happy with that so far? Thank you. Okay, so the next 2 slides, I just want to quickly say what I mean by differentiate the PDE. Excuse me. Okay, so this part will be technical, okay? I'm warning you now, technical part coming up. 2 slides only, bear with me. Okay, a tutorial on how to differentiate the PDE. these PDE problems are very special in the sense that we can actually differentiate it to give us an idea of the norm. This is why we like these PDE problems, because with all the finance problems, we can't do anything with it. The theory doesn't apply anyway. With these PDE problems, we can. And to be able to estimate the norm of the PDE, we have to differentiate the PDE. So this is what I mean by differentiate the PDE. Okay, we have the elliptic PDE from before. We write it in weak formulation. So you have this weak formulation which says you have a test function W. For any test function, this equality holds. Any test function in the H10 space in the physical domain. And then you have the random parameter Y here appearing on the coefficient and the solution. But Y does not appear on the right-hand side. Okay. Regularity of the PDE with respect to X is well known to be not smooth. X is the spatial variable. The random field can be very rough. The solution of the PDE might be not smooth. It may be at most once differentiable. I think it's in H1. Solution is H1. Sometimes maybe H2. Okay, but here we are looking at smoothness with respect to the parameter Y. This is our random parameter, right? So how do I differentiate the PDE? Okay, so we want to find out what's the mixed derivative with respect to the parameter Y. Okay, so Y would be our random variable. And I have a multi-index nu. Imagine that as a vector, which says nu1, nu2, nu3, nu4, and so on. Nu1 tells me how many times I want to differentiate with respect to Y1. Nu2 tells me how many times I want to differentiate with respect to Y2, and so on. Okay, so I want to work out this mixed derivative of order nu of the left-hand side and the right-hand side. Okay, so left-hand side, I just put the derivative. I haven't done anything else yet. I put derivative here. The right-hand side becomes 0 because the right-hand side does not depend on Y. That's an easy first step. Okay, and step 2, I apply something called Leibniz product rule because I have here a product part that both depends on Y. So you apply Leibniz product rule to give you this formula which involves this multinomial. And then I'm going to be very quick, okay? This is just give you an idea. So we can make use of the formulation of the uniform case, which says that your coefficient is of a linear form. So you can actually work out exactly what happens when you differentiate. You substitute this in here, and then you separate out the zeros term, which is the special case, move everything to the right-hand side, and then you pick a particular test function, substitute it in, apply Cauchy-Schwarz inequality, do some estimations, and bang, you end up with a recursive formulation for the derivative of the PDE, and from which you can apply induction, and you end up with a bound on the derivative. That's it. Don't look any more detailed than that. Okay. That's my 2 slides of tutorial. I just really want you to get an idea of what we mean by differentiate the PDE. Okay. It really is basically this. You start with the weak formulation. We differentiate the PDE left and right. And because the right-hand side does not depend on the random parameter, in this case, this is just 0. And then you just do some manipulations to get an estimate of the derivative. But by doing this, we get an estimate of the norm of the integrand. And then we can apply the QMC theory. That's all. Okay? So tutorial is over to here. Okay, so I now want to just come back to a more higher level talk, just give you some idea of what other things we can do. So extensions to these PDE problems. First of all, in the log normal case, I mentioned that we have a series expansion in the exponent, right? E to the power of a linear expansion. So there are other ways to deal with the log normal problem. Instead of working with a series expansion in Z, which would have given you a value of Z for every possible position vector X in the spatial domain, you can say that I'm only interested in this coefficient at a finite number of points. Okay, so if you assume that I'm only ever wanting to know the Z value at Xi for finitely many points, then you can look at this in terms of a discrete matrix. an n by n matrix R. Rather than having a covariance function which codes for every point in the spatial domain, you can have a covariance matrix which gives you precisely the field at those discrete points. If you're happy to live with that discretized version, then you can tackle this log normal problem using an idea called circular embedding. Basically, if you assume some spatial property of the covariance function and having some property of the grid that you work with, then it's possible to embed this matrix, which will turn out to be a toplet matrix or block toplets. You can embed that in a circular matrix to allow you to do a fast factorization and allows you to construct the field in a quick way using FFT. That's the idea behind it, again, without going into details. And another way to do this is also using a discrete factorization method, but make use of this H matrix technique. Using some iterative method to solve this using a theory of like Krylov subspace and so on. And other extensions of these PDE work, so I should also mention, so I didn't say much more about that because Ian will talk about generating random field the circular way on Friday morning. So he will devote the talk to this topic. Other things we also try to work on, also in the direction of QMC for PDEs, is to apply it to some PDE eigenvalue problems which appear in neutron diffusion and also even neutron transport. And also, we try to work together with Ganesh, who is here. We've tried to work on applying QMCs to some wave propagation models. So the PDE uniform case, PDE uniform and log normal problem I talked about before, can be formulated in a more general way that applies to not just the elliptic PDE that I gave before. It can be generalized to other PDE problems. But there are some assumptions which are very technical and it may not be satisfied, very stringent assumption. And so this work will allow us to make use of some new formulation of the Helmholtz equation problem, which is sign definite. Is that the right word? So Ganesh is going to talk about the sign-definite formulation of the, the sign-definite formulation of the Helmholtz equation problem. And there are actually also many other work in the Bayesian inverse problem, and Christoph Schwab will be talking on Friday morning on using higher-order QMC methods for Bayesian inverse problems. So I don't have much time left. I thought I could go up to the end, but let me just try and get to this cost reduction part, because we have many experts here. And this part applies to the PDE problem, but also for other problems. Okay, just quickly, the uniform problem that I talked about before, we were able to apply using setting 1 and setting 3 to get higher order and first order. For the log normal problem, which lives in the Euclidean space, we have to use setting 2. So for the moment, there's no theory that allows us to get to higher order. Dirk Newens will talk on Thursday afternoon about using multivariate decomposition method combined with higher order method to get the PDE problems to essentially setting 4, but in a slightly different way because of this cost reduction, which I will quickly talk about. Okay, in the remaining 5 minutes or 4 minutes. So first cost-saving strategy I want to talk about is this multi-level or multi-index. And multi-level methods, Mike Giles is the expert here. Mike Giles should be sitting somewhere here. So we can talk to him about multi-level methods. In a way, multi-level method is like this. You write the function as the telescoping sum. So imagine this is an integration problem. You write the function as a telescoping sum involving more and more integration variables. The algorithm truncates this telescoping sum and then apply a different quadrature rule to each difference differently. Okay? The theory behind this basically says you have to choose a truncation level to make the truncation error maybe half of epsilon, and you choose your quadrature methods to make the sum of these quadrature paths also epsilon on 2 so that the total error is epsilon. Okay, and the idea is that maybe the successive differences get smaller, so you will use smaller number of samples for these high dimensional problems, and overall the cost is reduced. That's the idea of multi-level. Multi-index is an extension of multi-level, but you take into account multiple aspects of the problem. You do multi-level to many things at the same time. Okay, and Peter Yan this afternoon in the poster is going to talk to us about how you combine multi-index with QMC, right? Yes, okay. And also with Mike, we look at combining multi-index with sparse group methods, for example. MDM, we have quite a few experts here on working on MDM here. So Greg is here, Dirk is here, and Alec, my PhD student, will be here this evening. So the multivariate decomposition method is similar to multi-level. But what you do is you write the function as a sum of terms, each term depending only on a small number of variables. So already this morning, I think in all 3 tutorials, we talk about ANOVA decomposition. Here, I specifically want to focus on something called the anchor decomposition. ANOVA decomposition requires you to integrate the function to get the terms. Anchor decomposition, you don't. Okay, I'll come to that. So the idea is similar. You have an infinite sum here, which we will then choose a set we call the active set. So you only work with a smaller set of sets, and you apply the quadrature approximation to each of these terms. So the general idea is, again, the same. You have a truncation error coming from the parts outside of your active set, and then you have this quadrature part which you try and control. And the idea is that you have some control on the size of these individual terms so that you know how to choose the right quadrature method and you construct these active sets. So Greg's talk on Wednesday afternoon will be about constructing active sets, or more in general about infinite dimensional integration problems. And so implementation, so we are actively working on efficient implementation of this MDM algorithm. Basically, we make use of the anchor decomposition. So with respect to the anchor A, Fred's talk about anchor of 1. So it's a similar idea. And this is being applied to the PDE problems as well, which Dirk will talk about on Thursday. I think I run out of time. So this is another cost-saving strategy which makes use of the structure in the quasi-Monte Carlo point sets. So I need to skip that. And it applies also in these PDE applications as well, but more in general to other applications too. Let me skip all that. So software, so in this review paper with Dirk, it comes also with an accompanying software package where we try to capture the special features of these PDE problems and specify that the special structure of the norm of the integrand from PDEs, and if you can feed those structure into the construction script, it will give you the generating vector or generating matrices, but they are also in general more the point generator codes for getting to these, including the interlaced SOBO. So this is giving you higher order QMC method. So if you don't want to worry about the theory of higher order QMC or any of that, you just want to try out QMC method first, then what you could do is you could just download the SOBO sequence generator with the generating matrices that allows you to go to higher order. Alpha 3 means you can get third order convergence rate. Use the generator, sample your points, and then try your integrand and see whether you get third order, and so on. You can do this without doing all the theory first. And I would suggest you actually try the numerics before you worry about the theory, because sometimes it works very well, like in the finance problems, but we still have a lot to catch up from the theoretical side. Okay, I think I'm now out of time. Thank you. They are not bounded. So what happens is we generate the points in the unit cube, which are bounded, and then we use the inverse cumulative normal mapping. So you have phi inverse, which maps 0, 1 to the Euclidean space. So it's not bounded, but it will have the distribution of the normal density. Yes? Okay, from the theoretical point, it's not completely sensitive, except in 2 ways. first of all, for the convergence rate, we want to be able to prove that everything is independent of dimension. We need our variables to be ordered from the most important to the least important. So the variables are already ordered. X1 is the most important, X2 is the next important. And so when we do this component by component, essentially we start from the most important. And another way to explain this is because this is CBC, you keep fixing what you have done before, the number of choices become more and more and more limited. So for two reasons, it is actually fixed.
We assume the first ones are more important.
Yes, but from the theoretical point of view, with the weights, what we need is the weights to be summable. So you really need to put the important ones first, and then it would be summable. Different time step. I have not worked with anything which is to do with time. So how would that work? The problem we're working on, Ganesh, with the wave problem, we also don't have time dependence, right? I think maybe this.
If you want,
we probably need a microphone.
To discuss, we need everybody to understand. Maybe you raise up and talk very, very loud.
Yeah, the question is to do with if we have a wave problem with time dependence, whether this construction of lattice through this QMC theory is going to change much, applying to a time-dependent problem. So I don't quite know, because our theory does not. We design QMC with respect to the parameter y, right? So y is the independence part. X is the physical variable. It's also kind of separated from our y variable, if you know what I mean. So t would just be another. Would that be the right?
So I guess I'm just curious, sort of if you didn't have regularity, I guess sort of the classical example would be like conservation law, where you had like a shock forming in some finite time. I'm sort of interested if anything's been done with that anywhere.
No.
So even if your domain is moving with respect to time, which is the extreme case, we have done a recent work on that. I can pass the paper to you. So you don't need to regenerate the QMC points again. In fact, normally we talk about domain being fixed and then time changing. So this one is a moving mesh problem as well, in addition to a lot of things. So what I found was that you don't need to regenerate the points again. So it does work very well. So that's a bit surprising, but no theory at all.
Thank you.
Our next speaker and the final tutorial speaker for today is Clémentine Prieur. She's in Grenoble at the university there, and she's also doing research in a team at INRIA in Grenoble in France. And she's going to talk about sensitivity analysis and the relationship with quasi-Monte Carlo.
Okay, so thank you for the introduction. I don't know how to. And first, thank you for the invitation. The tutorial I will give now, it's a little bit different from the previous ones, as it's not focused on quasi-Monte Carlo, but rather on global sensitivity analysis. But of course, I will open some doors between both and some open questions. So I will start with an introduction just to place the context. So the context is very general. In fact, we want to do few assumptions on the model. We can say that we are working in a black box context. That is, here, our function, our model is denoted by M. And a priori, we do not have any assumptions on regularity on that model. And we have the inputs or factors, and at the end, we have some output. And one wishes to quantify the sensitivity of that output to the input or to some interaction of inputs. The model can be very expansive. It can need a lot of memory to be implemented. And the input factors, they can be scalar, vectors, but also functionals. And it's the same for the output. But in most of the presentation, I will assume that there are scalars, and the same for the output, just to see how it works. But it can be generalized easily. I will first show a few applications where we can need sensitivity analysis. The first example is an application to a biogeochemical model. It is an ecosystem model of the Ligurian Sea. So you see that the Mer de Ligure, the Ligurian Sea, is here near Italy. And what we are studying is a model which is a coupled of two models, an hydrodynamical model with a biological model. And for these models, so the hydrodynamic model is a 1D vertical simplification of primitive equations for the ocean, and we have 5 state variables. And the ecosystem model is a biogeochemistry model, and we have 12 biological state variables. And in that study, we have a lot of inputs. We have 87 scalar input parameters. And the outputs are spatiotemporal. And the main issue in that study is how can we do calibration of the model. And for that, we use sensitivity analysis as a preliminary step for calibration. But another example, it's an example of agroclimatic model for the water status management of vineyard. It was a joint work with INRA, which is a research center of agriculture in France, and ETK, which is an industry on helping people making wine to take decisions to make some specific products. And in that case, the inputs were various natures, because we had some scalar parameters, such as soil texture, rooting depth, and a lot of other scalar parameters. But we had also some parameters which were describing the weather, and for that parameters, they are spatiotemporal. And some of the parameters were also correlated because, for example, for the texture, you have a percentage of different ingredients in the texture, and you know that the percentage are summing to 1, so that we are working in a simplex and not in a hypercube. So there are several difficulties that we have to handle for that problem. And in that problem, the objective was to use sensitivity analysis to help to a decision for industry. And that example is also interesting because sensitivity analysis is used for at two levels. So it is an application to integrated land use and transport models. And in that case, we need sensitivity analysis first to calibrate the models, which are very complex. And we also use sensitivity analysis. Once the model is calibrated, we need sensitivity analysis to test several scenarios to see if the various ecological scenarios have a lot of influence, if the parameters have a lot of influence for these scenarios. So you have two levels for sensitivity analysis. And the last example is the following one, which is not so far away from what Frances talked about, because here we have a problem which is the boundary control of an open channel. And for that problem, the model is not completely black box, because we know that it is modeled by a PD, shallow water equations. And what we have is that these shallow water equations are controlled by boundary conditions, which are the opening of a channel, upwind and downstream. And this control is written in terms of various parameters. So, for example, the friction slope, and these parameters are uncertain, so that we want to make some sensitivity analysis, but as we have a PDE, which depends on random coefficients, we can make some intrusive, use some intrusive tools, such as Galerkin projections to get some implementation of the model, which are very fast, and then to plug in it in the sensitivity analysis. So there are different examples of applications, and what I will present now can be adapted to each of these examples. So the outline of the tutorial will be the following. So I first will introduce the sensitivity analysis framework in the in the case where the inputs are scalars, the output scalar, and where we have some independence between variables. Then I will explain how we can estimate the sensitivity measures. And we will also see that we can have a recursive estimation procedure because the aim will be to design the experiments in a sequential way, so to be able to reach a precision for the sensitivity estimation. And then I will open a few questions. Okay, so the context is, as I said, you have D input. So it's okay because here, just I consider X living in RD, and the output is scalar, and my model is denoted by M. And as I said, I want to determine the way the output of a model reacts to the variation of the input. And you have several types of sensitivity analysis. First, you can make a qualitative analysis. You want to know if some parameters are not influent. Can we fix it from the beginning? And in that qualitative studies, we do not need to rank the different parameters. We just want to have an idea which parameters are the less influent. And most of the time, it is the only analysis which are affordable when we have a very, very limited budget. And then if you want to go further, and if you have the budget for that, you can want to make a quantitative analysis, which leads to factors hierarchization. and, for example, to some statistical hypothesis testing, like the null is the I factor has no influence on the output. And for that, you need some sensitivity measures, and the budget will be higher, as we will see. And then, if you want to make a quantitative sensitivity analysis, you once more time, you can split the approaches in 2 directions. First, you can make some local analysis. So the main idea is that you will write your model with a Taylor approximation at order 1, and then you use the first derivatives as a measure of influence of the ith input. So the advantages is that the cost is independent of the dimension D, if you can derive an adjoint of an automatic adjoint. But there are some inconveniences, because of course it is a local approach, and it is not appropriate if you have very highly nonlinear models, as it is the case for ocean, for example, or many other applications. Then you have global approaches. So the idea is that the uncertainty and the input will be modeled by random variables, by probability measures. If the inputs are independent, it means that you have to choose a probability measure per input. So for example, here you have a unimodal Gaussian, and here a bimodal for another parameter. So the choice of this uncertainty is driven by the applications, and you have to exchange a lot with practitioners to know what is the uncertainty. If you have some measures, it can be a good choice to take a Gaussian where the mean is the measure and the variance is related to the precision of the measure. But this is a task in itself, the choice of the modeling of the uncertainty. And then, so you see that in the local approach, I just look at what happens around X, and it gives me a local information. And here I look at what happens on the whole distribution of the input. And as the inputs are modeled by random variables, then the output is also a random variable. Okay, and you can also have some measures which is in between local and global. What I mean is that you can look at the first derivatives and take the expectation over the distribution of the parameters. Or you can also consider the same with the square of the first derivatives. So what are the advantages? The advantages are the same as for local approaches, is that if you have an adjoint of your model, then you have a cost which is independent from the dimension. But the inconvenience is that it is not enough discriminant. If you look at both these models, the measures will be the same, but you see that the behavior is rather different. But in fact, these measures are interesting because they allow to make some screening, because they are related to the measures I will provide you now with inequalities, and it can be used as a qualitative approach, but not really as a quantitative approach. Okay, so I will now focus on what are called Sobel indices. That is that I will use global sensitivity analysis based on the variance decomposition we have seen in most of the tutorials. And what we assume, and is very important for that approach, is that the uncertainty and the different parameters are independent. And I will say then what we can do when we have some dependencies, but that is not so easy if we have correlations between the uncertainties. So we want to know if the output Y is varying less or more if we fix one of its inputs. That is, we are interested by the variance of Y if xi is fixed to a nominal value, small xi. But the question is, how can we choose small xi? Because we do not want to be local. We will have to take the expectation. So we consider the expectation of the conditional variance. And the more this quantity is small, the more fixing xi reduces the variance, so that it means that the input xi is influent. And then what we use is the total variance decomposition. That is, the variance of y can be decomposed as the variance of the conditional expectation plus the expectation of the conditional variance. And the Sobol indices are then defined as the variance of the conditional expectation divided by the variance. And this quantity, due to the total variance theorem, is between 0 and 1. And due to the interpretation I gave you just here and the total variance theorem, this times it means that if Si is close to 1, the ith input is influent. Okay? And these are called the first-order Sobol indices. And if you take a very particular case where your model is just a linear model and the xi are independent, we just recover that Si is rho I square, where rho I is the linear correlation coefficient. So it is coherent with what we get with linear models. And we can generalize these indices to any interactions. So for that, we use the Sobol Hoeffding decomposition. That is, if we have a model, we assume that it is square integrable and the hypercube. Then we can decompose M with a mean effect, first main effect, second order interactions, and so on until the d order interaction. And of course, we have a lot of such decompositions, but if you add some constraints, that M0 is constant, and you add also this constraint here, which is an orthogonality constraint, you get that the decomposition is unique. The consequences of the constraints is that M0 is just the mean of the model over the hypercube, and all the terms in the decomposition are orthogonal. And now, we can also derive from the previous formula the computation of each term of the decomposition. So, for example, if we want to compute the main effect for input xi, it's just the integration of the model with respect to every parameter, with respect to all parameters except the ith one, and we remove the mean term. And it's the same now for the second order interaction. You integrate the model over all the inputs except the couple, you have fixed, and then you remove the mean term and the first order effect. And so you can compute all the terms in the decomposition sequentially. So you see here that the decomposition is just the computation of multiple integrals. And then the variance decomposition. So I recall that we have modeled the uncertainty of the inputs by random variables. So, and we are in the case that we suppose that these variables are independent. We just need independent. So here, not necessarily following the same law, but let us say now just they are independent and uniformly distributed on 0, 1, so that we apply the decomposition to x, the random vector, and we have an interpretation of each part of the decomposition as expectation and conditional expectations. And then we take the variance, and due to the orthogonality of the decomposition, we get a decomposition of the variance. And you see here that the independence of the input is very important. Otherwise, you will have some covariance terms, and this decomposition would not be exact. And from this decomposition, we can extend the notion of first-order Sobol indices to any order interaction. For example, for the second order, if you have I different from j, the Sobol index for the interaction is just the variance of mij xi xj divided by the variance of y. And due to the orthogonality, it can be decomposed as you can see here. And what is important is that all these Sobol indices sum to 1, so that the interpretation is very easy, and you can rank the different influence for the main effect, for the interactions. You can get a ranking of these influence. And you can also study what are called the total indices. That is, you sum for all U containing I, you sum the Sobol indices SU. So you get the influence of the ith input due to its main effect, but also due to its interactions with other parameters. And the total index is a sum of Sobol indices, but you can also write it in a very convenient way. If you consider this notation, x minus I is just the vector x, where you remove the ith component, then the total Sobol index is just 1 minus the variance of the conditional expectation, where you condition with respect to x minus I. So it's important, as we will see later, for the estimation, because it means that we can estimate total Sobol indices with a cost similar to first-order indices. So just to summarize here, here you have different parameters, A, B, and C. Here the second-order interaction, here the third-order interaction. And the total effect of A is just the effect of A with B and A with C, and the third interaction. And now you can also consider the indices by group. In some cases, it can be interesting. So, for example, if you consider as an elementary step A, B, and AB, then the total effect for the group AB is all that combinations. Okay, so, but the problem is that these indices are, most of the time, they are not analytically available, so that we need to estimate them. And you have several approaches, so either you do not know, you know nothing about your model, sorry, so that you have to go to Monte Carlo approaches, and if you have some regularity assumptions, then you can go to spectral approaches, and then it can be more efficient, as we have seen with other tutorial. You can get very, you can get rates of convergence which are improved. In case the model is it's too heavy in terms of computation time, then you can also use some meta models. So you can use, for example, Kriging meta models, so Gaussian processes meta model, non-parametric regression, polynomial KO, anything you want, and then you can use this meta model to estimate Sobol indices. And for some meta models, you can get some analytical expression for the Sobol indices. It is the case, for example, for polynomial KO expansions. And for other one, you will have to use Monte Carlo to estimate the Sobol indices. But as your meta model is very quick to implement, it will be much faster. And just before going to the estimation, what happens for dependent input? You can find several alternatives in the literature. So first, you can, if it is possible, you can handle independent groups of dependent inputs. So, for example, if you remember the example where I have a texture and you have a percentage of different elements, maybe it's enough to consider the influence of all this texture, not going into the detail of the texture. You can also reparameterize the problem, and here I think we can make some links with active subsets or other things, but the problem is that if you reparameterize the problem, then for some practitioners it's not good because you lose the meaning of each input. Sometimes, even if you make a linear combination of several inputs, it's not good for practitioner. It depends on application field, but sometimes they really want to keep the meaning of each input and not to have some combinations. So, but it is a solution. And you can also relax the constraints and the functional decomposition. That is, you can get a hierarchical evening decomposition. That is, you get a decomposition where the terms are not orthogonal anymore, but you have only some orthogonality, only some of the orthogonality are preserved. But the problem with that approach is that the sensitivity indices that you get are very difficult to interpret. So a last alternative, and maybe I will have time at the end to say some more precise words about it, is an idea coming from economics. So you can see the problem as an allocation problem. That is, you want to have only one index per input. You won't have the first or the main effect and the second interaction effect, but just one index per input. And this index reflects the best allocation you can do for the variance decomposition. So if I have time at the end, I will go in the details, but otherwise, this is on the slide, so you can also read it. So let us go to the estimation procedure. As I said, we cannot compute the indices analytically, so we want to estimate them. So I need some notation. So X is the model for my parameters. And I consider X1 and X2 two independent copies of X. And then for I between 1 and D, I define Xi2, which is the vector whose components are the one of X2, except the F1, which is the one of X1. So in some sense, I can say that it is that I take X1, I freeze the ith component, and I resample all the other components. Then Y denotes M evaluated on X1, and Yi denotes M evaluated on Xy2. Okay, and if the random vector X has independent components, then I can write the Sobel index as this ratio, that is the covariance of Yi divided by the variance of Y. In fact, it is just the linear correlation coefficient when I consider the regression of Y on Yi. And then to estimate the indices, I need some samples. So now I is in 1D, and J is between 1 and N is the number of samples I need. So Xj1 is just distributed as X1, and Xij2 is distributed as Xi2. And then I evaluate the model on all these points. So that is, we have 1 plus D times N evaluations of the model. And the estimator is the following. So what do? If I come back, I have here a covariance divided by a variance. So it's very simple. I just take an empirical counterpart of this expression. And here is one way to proceed. It's not the only one. I can take any estimator for the covariance and any estimator for the variance. There are some differences, but it's not the topic of the tutorial. So I get an estimator which is close to that one. And this choice has good properties in terms of efficiency, but you can take other choices. And then, what is the main issue of that approach? The cost is prohibitive. Why? Because if I want to estimate all the first-order Sobel indices, we have seen that we need 1 plus D times N model evaluations. So it is linear in the dimension. So if we increase the dimension, we will have some troubles. And if one wants all the second-order Sobel indices, then the cost is even higher. Okay? In fact, this can be outperformed for second-order indices. The best with that approach, you need a cost which is linear in the dimension to estimate all the first, the second, and the total Sobol indices. For that, you can use some combinatorial tricks in order to reduce the cost to that formula to a linear cost, but it is still linear. So we can see here what happens. So with a star, we have the xj1, sorry. And with a bullet, red bullet, you have x1j2. So you can see that here you have frozen the first component. And on the right side, you have frozen the second component. Okay? But can we do better? That is, we would like some designs which allow to freeze each in each direction. For that, we will use the notion of replicated designs of experiment. So I consider a design of experiment, so it's just a matrix. We have n lines which correspond to the endpoints and d columns which correspond to the d input parameters. And d prime is said to be replicated from d if d prime can be written as follows. That is, I use a permutation, a column permutation for each input. Okay, so I have an initial design, and I use a permutation for the first column, a permutation for the second column, and so on. And if I consider such designs, what you can see, so D and D prime are two replicated designs. And we see that that time we have frozen not only the first component, but not only the first component, but also the second component. Okay? Each time I have a point in my initial design, I can find a point in the other designs which has the same first component, but I can also find a point which has the same second component. And that property is very important because we can estimate, it means that we can estimate all the first sensitivity indices using only two samples. So here it is what we obtain if the first design is just an independent sampling, but then we have troubles, as you see, because we have clusters and points are just do not well behave in the hypercube. But you can use a Latin hypercube sampling for the first design, and if you replicate a Latin hypercube, you get a Latin hypercube, so that here the discrepancy is better. So it is what is written here. You can use, here it's a Latin hypercube sampling, and if you if you use a permutation for each column, you get the second design. And then what is important is that you can use the estimate that I presented previously. What we want is that if we want to estimate, for example, the first order index for the ith component, we want to freeze the ith component and to resample all the other components. And in fact, this can be done with these two designs, just using a permutation of the lines. And it's good because a permutation of the lines, it means that we do not need further evaluation of the model. Okay, because permutation of lines is just that we consider the points in a different order. Okay, so with that idea, we can estimate all first-order Sobol indices with only two designs, and we get a central limit theorem for that, and the variance is reduced with respect just to taking IID sampling. And the question is, can we extend this idea to higher-order interactions? So if we consider second-order interactions, we need some structure on the design which is similar to Latin hypercube sampling, but which preserves the couples of columns. And the good structure for that is the two orthogonal arrays of strength 2. So here I recall the definition of a T, Q, D lambda orthogonal array. So an orthogonal array in dimension D with Q levels on strength T less than D and index lambda. It's just a matrix N times D such that in every n by t submatrix, you get all the q to the power t possible rows. So if you take some orthogonal arrays of strength 2, then you can mimic what we did for first-order indices. So we can use a permutation for each column. We still have an orthogonal array of strength 2. And then we can use a recombination of the points, which ensures that you have frozen that time 2 components. So it is what is written here. So it means that with 2 orthogonal arrays of strength 2, I can estimate all second-order sensitivity indices. So I don't have anymore the relation, the link with the linear, with the dimension d. The cost is independent from the dimension. So it is very interesting, but what, so first I will explain what the best we can do and what is the issue of that approach. So using a strength 2 orthogonal array, so you need 2n model evaluations for all second-order Sobol indices, and you can also get Q is the number of levels, so you can get Q times factorial Q estimates of each first-order Sobol indices. So, but if you take, you cannot take all these estimates. There are too many estimates. But if you choose randomly some of these estimates, you can reduce the variance of estimation by taking the mean of all these estimates. And now, if you use an orthogonal array of strength 2, and you use the combinatorial tricks of Saltelli, that time you have a linear cost, but it allows to compute all the total indices, all the second-order Sobol indices, and so many estimates of each first Sobol indices. So the main issue is for the total indices. You see that if you want total indices, you need that cost which is linear in dimension d. And actually, it is an open question if we can remove this dependence. Okay, so I think I have no many time for that application because I want to go further, but it's just the estimation, which we can give some bootstrap confidence intervals for the estimations. And so it's very efficient if you have a limited budget and if you assume that higher order interactions are neglectable, you have a cost which is independent from the dimension. But what would be interesting is to get some recursive estimation, because sometimes you have an estimation and you say, oh, I have new budget, so I want to increase my number of points. And for that, I need some recursive formula for my estimate. And also, a recursive estimation is interesting to avoid storage issues, because for many applications, the memory you need for your Sobol procedure is very high, and it would be interesting to have something which is just incremental. And in fact, it is the case if we consider the estimate I provided you before. We can write a recursive formula, which is the following. So that you can add a new point and you don't have to recompute everything. So here is the formula if you just add one point, but you can generalize it by adding some block of points. And you can also use overestimate, so it's not connected to that particular estimate. You can use over ones that are in the literature. So that it is interesting now to have some nested designs. And as I said, the more efficient procedures are based on Latin hypercube or on orthogonal arrays. So we want a way to increase Latin hypercube or orthogonal arrays. So for Latin hypercube, we can use the construction due to Kian. It is a construction which allows nested Latin hypercube samples. That is, you fix a big Latin hypercube sample, And then iteratively, you increase first the level will be increased progressively, but you have to fix an initial Latin hypercube at the beginning. And for second order indices, so you need nested orthogonal arrays of strength 2. And for that, we have a construction which is based on blocks of orthogonal arrays. But we will see later, but we don't refine the level at each step. We keep the same level, and we just choose randomly how we choose the points in the orthogonal array. So I think I don't have time to go in the detail, but this is a procedure for nested Latin hypercube due to Kian. So the smallest number of points per layer is obtained with this choice. That is, at each step, you have an exponential increase of the number of points. So it is a drawback, but it is due to the procedure. And I don't know if we can do better from now. So here is the first step. So as I said, you have to choose number of levels for the final step. And then you choose the 3 first points, and you refine with the red one. So you see that you have a refinement, but you still have a Latin hypercube. And then you refine once more, and you have green points. But at each step, you keep the Latin hypercube structure, okay? So that you can estimate the indices iteratively. For the orthogonal arrays, in fact, if you remember the definition, you have the index, which is important. And the idea is to construct blocks of orthogonal array of strength 2 with index 1. And at each step, you add a new block. And for that construction, you have 2 different approaches. So this is the geometric representation of the orthogonal array. Okay, you have to select the sub-hypercubes. And the first approach is an algebraic construction. That is, we know from coding theory that you have a collection of orthogonal arrays which form a partition of NQD. So you know the size of the collection. And at each step, you pick randomly in the collection. So it is the first approach. And the second approach is an accept-reject construction. So at each step, you construct a randomized orthogonal array, and then you have to test if the block is different from the previous blocks. So it has a cost, but there are 2 alternative approaches to construct iteratively orthogonal arrays of strength 2. And then if you want to compare their properties, you have to look at criteria. So for regularity, for example, the mean dist, or for uniformity, so the discrepancy we have seen in many tutorials. And here it is a comparison for Latin hypercubes. So in green you have nested Latin hypercubes, in yellow Latin hypercube, and in red the uniform. And you see that even if your nested Latin hypercube is not optimal, it does not. It is very close to the Latin hypercube sampling. So the fact to make the construction iterative is not deteriorate the properties. And then, this criteria was the mean dist. So the higher it is, the better it is. And here, the star discrepancy, so that time we want it to be small. And you see, once more, that the iterative construction does not deteriorate the properties. And for orthogonal arrays, so that time we have uniform, big orthogonal array, and then the 2 nested construction, the algebraic one in green and the accept-reject in blue. And it's the mean dist, so you see that the best construction for the mean dist is the algebraic construction in green. It is better, even better than the orthogonal array, not iterative construction. And if you look at the discrepancy, that time the best one is the non-iterative construction, But we see that with the two nested constructions, they are similar and they are not so bad because they are close to the non-iterative construction and they are better than uniform construction. Okay, so I had a few questions to ask, and they are open questions. So it might be more efficient to use Sobol or other digital sequences as design of experiments if we add some further regularity assumptions. And in the same way, we need an iterative construction. And the question is that the usual constructions need to double the number of points at each step. And we can have some additive approaches, but we lose the property, the digital property, in fact, and it is based on group algebra. And the main drawback is that you have correlation between the blocks you select, and in fact, it's not so good. So to be more precise, so in red, it's the Latin hypercube design. In blue, it's the iterative construction, the iterative construction for Sobol sequences, which is additive. And in green, it's the iterative construction, which is multiplicative. And you see that we have a gap. If it is additive, of course, it is better because I just add a number of points, a fixed number of points. So it has some advantages, but we see that it's not so efficient. And here it's the same. So for the Maximin criteria. So the question is, can we do better? Can we have an additive construction which provides some good properties? And then, so as we have seen, QMC properties are relative to effective dimension. And because in the other talks, you have seen that to know which are the, if you have a low effective dimension, you compute the ANOVA decomposition. And here, I want to do that thing in the other side. That is, I want to know if the effective dimension is low in order to get good designs of experiments for my ANOVA decompositions. So it's in the other way, in fact. So in some sense, it's not so easy because it seems that if we need to make a sensitivity analysis before knowing the effective dimension, it's not very efficient. And maybe it is possible to use active subsets to tune the QMC. So active subsets, in some sense, are very close to the indices I presented at the beginning, which are the expectation of the first derivatives. So they are not so discriminant as Sobol indices, but they are very quicker to evaluate. So maybe it's a good compromise to use active subspace instead of Sobol indices in order to find the good effective dimension. Okay, so it is also an open question. And then the question is about the optimality criterion for the estimation of Sobol indices, because it was already mentioned in the previous tutorials. What we want to estimate is not an integral, but it is a function of several integrals. And for the moment, what is used is you have a bound for the error in the computation of each of the integrals arising in the Sobol estimation. And you deduce a bound which is not optimal. And a way, there exists some other bounds which are more efficient. That is not just a bound on the estimation of integral, but of a function of integrals. I'm not sure if I am clear, because what you have when you make Sobol indices estimation here, that corresponds to the estimation of an integral, that corresponds to the square of the estimation of an integral, and the same for the denominator. So we would like a criterion which fit better that types of problem. So it is also an open question. And I had several slides on Shapley effects, but I don't know if I have time, maybe that. Pierre? No, maybe. Okay, so if you are interested, it was just a few open questions on Shapley values, which are alternative in the case of dependent variables. So yes, I have time, okay. So as I said, when you have dependencies, the Sobol indices are not well suited. You can estimate them, of course, if you can sample from the initial distribution, which is not a product anymore. But what is the meaning of these indices, we do not know. So instead of that, we consider the Shapley setup. That is, we consider that U, the set of indices, is a team which create a value of U, and the total value is the value of 1 to D. And then we want to make an allocation, that is, we want to attribute phi j to each input parameter. And we have some axioms, which are the Shapley axioms. First, the efficiency. We want that the sum of each allocation is the total value. We want also that if the value of u intersect with I is equal to the value of u for any u, it means that the ith input is a dummy variable. We also want some symmetry. The value of u intersect with I is equal to the value of u intercept with j for any u. Then it means that phi I is equal to phi j, and we need also some additivity. And Shapley showed that you have a unique solution to that problem, and the solution is given by that formula. And now we consider that the variables x1 until xd, so the d parameters are the team members, and they try to explain the model M. And the value of any subset is how much can be explained by that set of inputs xu. And if we choose the value of u as the sum of the Sobol indices SV for v included in u, then the corresponding phi j are known as the Shapley effects. So this idea was introduced by Art in 3 years ago. And if you have independent inputs, the interpretation is very easy. The relation between Shapley and Sobol indices is very easy. Shapley is just that sum of Sobol indices renormalized by the size of the interaction. And for dependent input, this last formula is not true anymore, but Shapley effects are still meaningful if one wants to fix some variables which are not influent. Because it is a good way to allocate the part of variance, taking into account both the interactions and the correlations, which is not so easy. Because with other indices, for example, with hierarchical orthogonalizations, the problem is that the allocation of the correlations was not fair between all the components. And the problem is that, as we have seen during this tutorial, estimating Sobol indices has a cost. And here, you see that you want to estimate all these differences, so it is more costful. You can use meta-modeling, of course, but it has a cost which is higher. Even if you use combinatorial trick, the cost is higher than for Sobol indices. And an open question is that possible to mimic some game theory algorithm to estimate this Shapley effect? I know there are some algorithms, but with very specific values, Shapley values. And if we consider as Shapley value this one, which is well adapted for sensitivity analysis, is it possible to get some efficient algorithm? Okay, and here all the person I want to thank, so the organizer, Shu McDonald, and all my co-authors on that work.
I'm not familiar very much with the Shapley theory, but as far as I'm aware, it applies for matching problems, right?
Yes.
And that's the same Shapley theory that you're using. Is there possibly any relation between this matching problem and some kind of game theoretic thing where you have a two-player zero-sum game? Could you formulate optimality criteria in terms of such things?
Yes, it is. Shapley values are used in game theory, and it is why. And they have very specific algorithm, but most of the time, the choice of the value is very important. And that value that was introduced by Art is very specific to sensitivity analysis. And what the algorithm are doing right now is that in the algorithm, you have to estimate this value. And this is what is costful because it is a variance of conditional expectation and the cost is high.
Thanks.
Yes. Okay, so the problem with anchored, it's very quick to estimate, but it's not an orthogonal decomposition. So what I have seen in the literature is that people use some what is called ANCOVA decomposition. So you add the covariance in the decomposition, but then the problem is how can we interpret the indices that we get? It's the same as I said, in fact, it is in that family of methods. Sorry. Up. Okay. Here, if I relax the constraint, for example, it's the same. I have some decomposition, which is not orthogonal. It's the same for anchored ANOVA. And I can get subtle indices, extended subtle indices, taking into account the covariances. But the covariances are not well allocated. I mean, if I need sensitivity analysis to fix some non-influent factors, it's a problem because if I have more than 2 variables, so in dimension 3, it's not easy.
It is not orthogonal in L2 space, but it is orthogonal in some other spaces. So maybe that could be utilized.
Maybe we can discuss, yes. Sorry?
I'm wondering whether, suppose I took a digital net, a digital sequence, and just kept increasing the sample size by powers of 2. Would that give me for free some nested Latin hypercubes, or is there something else I need to do?
Yes, it is enough to do like that for digital sequences. But if you want general Latin hypercube, the construction is, so I didn't describe it, but it is the one due to Kian. It is that one, okay? And I have to fix, the first step, I have to fix a high number of levels, and then I will refine progressively. Maybe we can discuss, but the construction is described in the paper of Kian, but the drawback is that it's not really a drawback because you can say the initial construction is related to my global budget. I know that I will never go beyond this budget. And then progressively you use some construction of Latin hypercubes. And the grid is finer and finer.
But I think if you start small and then keep doubling, usually when there's a budget, the first thing that happens is people go over the budget. Right? That's part of life. And then so you start with 16 and go to 32, 64, 128.
No, here what you have to do, you have to construct your whole design of experiment, but then you evaluate the model only on a few points, and then the double of points and power of 2 points. So the cost is not the whole cost, but you have to design a very big design, and then you evaluate on part of this design.